You live on a planet so small that more than 1 million copies of it could fit inside the sun. That sun is one of 400 billion stars drifting through a galaxy so enormous that light itself needs 100,000 years to cross it. But none of that prepares you for what sits right next door. Just 2.5 million light years away, a galaxy called Andromeda stretches across 220,000 light years of space and contains roughly 1 trillion stars. It dwarfs everything we call home. And right now, at this very moment, it is moving directly toward us. What follows is a journey through measurable distances so extreme they will systematically dismantle every intuition your brain has ever built about size, distance, and exactly where you stand in the architecture of this universe. Are you ready? Brace yourself. Let's begin. You think you know how big the Earth is? You have seen the photographs taken from orbit. You have watched the curved blue horizon and footage shot from the International Space Station. You may have flown across an ocean and felt, somewhere around the 6th or 7th hour of staring out that small oval window, a creeping, inescapable sense that this planet is genuinely, staggeringly enormous. And by every standard your body and brain evolved to process, you are right. Earth is immense compared to a human being. The scale of this planet dwarfs every biological system that ever formed on its surface. Mountains that took tens of millions of years of tectonic collision to build. Oceans that cover more than 70% of the surface in liquid water, averaging over 2 miles in depth. Deserts that stretch for thousands of uninterrupted miles across continental interiors. A planet that has been reshaping itself through volcanism and plate tectonics for 4.5 billion years. A world that had already hosted and extinguished entire lineages of complex life before the first member of our genus ever stood upright on an African grassland. That intuitive sense of planetary enormity, the breathless feeling you get staring at a mountain range or watching a storm system consuming an entire coastline, is the first thing we need to carefully, methodically dismantle. Because once you start measuring Earth against the objects that surround it in space, something deeply uncomfortable begins to happen. The planet you stand on, the world that contains every city, every ocean, every mountain range, every war, every love story, and every civilization that has ever risen or fallen, begins to shrink. And it does not stop. The shrinking accelerates. Every new scale you apply removes another layer of significance, until the thing that was so enormous it contained all of human history is the thing that cannot be found without a magnifying glass. Let us start with what you can actually touch. The circumference of everything you know. The circumference of Earth at the equator measures approximately 24,900 miles. That is a verified number. You can confirm it with GPS satellites and geodetic survey data accumulated across decades of measurement. It is real, fixed, and precise. But there is a vast difference between a real number and a comprehensible one. A number can be correct without being experienced. So let us make this physical. Let us translate it from a figure into a feeling. If you climbed into a commercial airliner, flying at a standard cruising speed of around 550 miles per hour, and you never landed, never stopped for fuel, never circled around storm systems or waited for clearance to enter foreign airspace, it would take you just over 45 hours to circle the planet once and return to your departure point. Nearly 2 full days of continuous, non-stop flight just to trace the outline of the world you were born on. That is the Earth measured in the fastest transportation most human beings will ever experience. If you attempted the same journey in a car doing 70 miles per hour on an impossibly straight highway that wrapped seamlessly around the equator, the drive would take roughly 14.5 days. 2 full weeks of driving, without rest, without sleep, without stopping to eat or refuel, just to circle the planet once. 2 weeks. The circumference of a single rock floating in space would consume a fortnight of continuous, unbroken travel at highway speed. That is Earth measured at human speed. And it feels enormous, because for a species that spent the vast majority of its evolutionary history walking at 3 miles per hour across African grasslands and forested river valleys, it genuinely is enormous. Your legs were never designed to accommodate this planet's scale. Your intuitions about distance were calibrated over hundreds of thousands of years, spent navigating territories that rarely exceeded a few hundred square miles in a lifetime. River crossings, seasonal migrations following herds, the arc of a day's walk from a sleeping site to a waterhole and back. That was the relevant scale for human cognition for most of human existence. And Earth was built on a scale that exceeded all of it by orders of magnitude. When the earliest anatomically modern humans began their long dispersal out of Africa approximately 70,000 years ago, the journey to the southern tip of South America, the last major landmass to be reached, took something in the vicinity of 10,000 years of gradual, generational migration. 10,000 years of human beings moving, stopping, settling, having children who move farther, having grandchildren who move farther still, pushing incrementally across connected landmasses and across open water on primitive watercraft, generation by generation, toward a destination none of them could conceive of, and no individual would ever see. 10,000 years to cross what was, from the planet's perspective, less than half of its surface area. Earth was built on a scale that simply did not care about biological travel times. Now go vertical. The deepest scratch. The deepest point in Earth's oceans is the Challenger Deep, located within the Mariana Trench in the western Pacific Ocean. It plunges to approximately 36,000 feet beneath the surface. That is nearly 7 miles straight down into the seafloor. 7 miles of vertical descent into an environment so extreme, so utterly alien to the conditions in which all terrestrial life evolved, that it might as well be another world. At those depths, the water pressure exceeds 16,000 pounds per square inch, approximately 1,000 times the atmospheric pressure you feel standing at sea level. The weight of the entire water column above, pressing down on every square inch of surface at the bottom, is enough to crush conventional submarine hulls the way a human hand crushes an aluminum can. The temperature hovers just a few degrees above freezing, in perpetual cold that has never once warmed since the oceans formed. Sunlight vanishes completely within the first 1,000 feet of the ocean's surface. Below that threshold, every last photon absorbed or scattered, the ocean exists in absolute, total, undifferentiated darkness. A darkness that has persisted, unbroken by any natural light, for as long as the oceans have been liquid. Fewer than 30 human beings, in all of recorded history, have ever reached the bottom of the Challenger Deep. Each descent required custom-engineered submersibles, built with titanium pressure hulls, calculated to withstand compressive forces that dwarf any other structure humans build. The vehicles are tested under conditions that exceed those of many conventional spacecraft. The occupants are isolated from the environment by a few inches of precisely engineered metal, separated from instant catastrophic death by a margin that has no equivalent in human surface experience. It genuinely sounds like a voyage to another planet. And in terms of sensory experience, the pressure, the cold, the absolute darkness, the alienness of the biology that has evolved down there in those crushing, lightless conditions. It is another world in every meaningful sense except one: distance. Here is the number that reframes everything. Earth's diameter is roughly 7,918 miles. The Mariana Trench, the single deepest structure on our planet's entire surface, represents a scratch less than 7 miles deep on a sphere nearly 8,000 miles across. To put that in terms, you can test with your own hands. If you shrank Earth down to the size of a standard basketball and held it, the Mariana Trench at that scale would be a depression smaller than a single human skin cell. You could run your palm across the entire surface of that basketball with the most sensitive fingertips in the world, and you would not feel it. The deepest point in the ocean, the feature that required the cutting edge of human engineering and decades of technological development to reach, the place that has been visited by fewer people than have walked on the moon, is at planetary scale a rounding error. It might as well not exist. This is the first lesson in cosmic scaling. It is a lesson that will repeat itself, with increasing severity, at every level of measurement we encounter from this point forward. Things you believe are immense, things that genuinely challenge and overwhelm human engineering and human survival, often turn out to be immeasurably small when you simply move one level outward and recalibrate your frame of reference. The Mariana Trench overwhelms human capability. It represents the frontier of human exploration. It is a genuine physical frontier that only a handful of people will ever experience directly. And to the planet it exists within, it is a surface irregularity too shallow to notice. Hold this pattern in your mind. At every scale we are about to visit, the thing that just seemed vast will be the thing that disappears. 93 million miles is just the beginning. We have not even left the planet yet, and already the scales are doing something uncomfortable to our sense of proportion. But let us leave. Let us step back from the surface and begin to measure the distance between Earth and the nearest object of any significance. Earth orbits the Sun at an average distance of approximately 93 million miles. Astronomers call this distance 1 astronomical unit, abbreviated AU, and it serves as the baseline unit of measurement for everything within the solar system. Every planetary distance, every comet trajectory, every asteroid orbit is first expressed in terms of this single reference point: how far we are from our own star. 93 million miles? Let us try, with full honesty about the likely futility of the effort, to make that number mean something to a human body. At the cruising speed of a commercial airliner, the journey from Earth to the Sun would take over 19 years of continuous, uninterrupted flight. 19 years in the air, without landing. A child born on the day you took off would be entering early adulthood by the time you arrived. Nations would have held multiple elections. Technologies you use daily would have been invented, popularized, and replaced by their successors. The world would be different in ways you could not anticipate, and none of that would matter because you would still be in the air. At the speed of a bullet fired from a high-powered rifle, roughly 1,700 miles per hour, you would still need more than 6 years to reach the Sun. 6 years at bullet speed. The fastest lethal projectile humans routinely manufacture, fired in a straight line, continuous and unimpeded, would require 6 years to cross the distance between Earth and its own star. And even light, the fastest phenomenon permitted by the known laws of physics, traveling at approximately 186,000 miles per second, requires 8 minutes and 20 seconds to make the crossing from the Sun's surface to your eyes. 8 minutes and 20 seconds. Think carefully about what that means in practical day-to-day terms. When you look up at the Sun, you are not seeing the Sun as it exists at this moment. You are seeing it as it was 8 minutes and 20 seconds ago. That is the oldest real-time image available to you of the most important object in your solar system. If the Sun were to catastrophically and completely vanish at this exact instant, gone, simply not there anymore, you would not know it for 8 minutes and 20 seconds. You would continue to feel warmth on your skin. You would continue to see light in the sky. Every sensation connecting you to the Sun would persist, perfectly unchanged, completely unaltered, for the time it takes to brew a pot of coffee and pour a cup. And then, without warning, the light would go out. That is how far away our own star is. It is close enough that its light reaches us in less than 10 minutes. It is far enough that its disappearance would go undetected for the length of a coffee break. But the distance is only half the story. The Sun, a thermonuclear furnace in your backyard. The Sun's diameter measures approximately 864,000 miles. To translate that into direct comparison, the Sun is roughly 109 times wider than Earth. You could line up 109 Earths side by side, equator to equator, and they would just barely span the Sun's full diameter from edge to edge. 109. If each of those Earths had a human being standing on its surface, they would form a line stretching from one side of the Sun to the other that would contain more than 109 billion people, more human beings than have ever lived in the entire history of our species. The Sun's volume is even more punishing to intuition. Approximately 1.3 million Earths could fit inside the Sun. Not beside it. Not in a ring around it. Inside it. Every continent, every ocean, every mountain range, every desert, every glacier, every city and road and building and organism on this planet replicated 1.3 million times over, and the Sun would swallow all of it with room left over to hold more. The object that rises every morning and sets every evening is not a gentle lamp in the sky. It is a sphere of superheated plasma so massive that it contains 99.86% of all the mass in the entire solar system. Every planet, every moon, every asteroid, every comet, every grain of interplanetary dust, every spacecraft humanity has ever launched, every bit of matter in the solar system, that is not the Sun, makes up the remaining 0.14%. Jupiter, The largest planet in our solar system, which could itself swallow over 1,300 Earths within its volume, is a footnote next to the Sun, a gravitational afterthought. Earth does not even register as a footnote. Earth is a speck of rock orbiting a thermonuclear engine that converts approximately 4 million tons of its own mass into pure, radiant energy every single second through nuclear fusion. Let that number settle. 4 million tons per second. Not per hour, not per day, per second. That is the mass equivalent of roughly 22,000 fully grown blue whales, the largest animals that have ever lived on Earth, annihilated every single tick of the clock, their mass converted entirely into electromagnetic radiation and neutrinos, pouring outward from the solar surface in every direction into the surrounding void. And the Sun has been sustaining this output continuously for approximately 4.5 billion years. Every second for 4.5 billion years. It will continue doing so for roughly another 5 billion years, before it finally exhausts its hydrogen fuel and begins the series of transformations that will ultimately see it expand into a red giant, shed its outer layers in a planetary nebula, and collapse into a slowly cooling white dwarf remnant, roughly the size of Earth. In the grand catalog of stars, our Sun is precisely, relentlessly ordinary. It belongs to the most common stellar category in the galaxy, a G-type main sequence star. It is not particularly bright. It is not particularly massive. It is not particularly old or young. It has no unusual features that would distinguish it in any meaningful way from hundreds of billions of comparable stars scattered throughout the Milky Way. The Sun is average in every measurable dimension, and at planetary scale, it is so enormous that everything humanity has ever built, every distance humanity has ever traveled, every measurement humanity has ever taken on the surface of this world is reduced to the scale of a sketch on the wall of a cathedral. Here is where the emptiness begins in earnest. The solar system. Empty space with occasional rocks. Earth sits 93 million miles from the Sun. Mars, the next planet outward, orbits at approximately 142 million miles. Jupiter, the first and largest of the gas giants, circles the Sun at roughly 484 million miles, more than 5 times Earth's distance. Saturn, with its famous ring system, drifts at 886 million miles. Uranus orbits at approximately 1.8 billion miles. And Neptune, the outermost of the recognized major planets, traces its slow path around the Sun at a staggering 2.8 billion miles from the center of the solar system. That is the span of the planetary solar system. From Earth to the outermost major planet, roughly 2.8 billion miles. A beam of light leaving the Sun takes over 4 hours to reach Neptune. A radio signal sent from Earth to a spacecraft operating near Neptune traveling at the absolute speed limit of the universe, 186,000 miles per second, requires approximately 4 hours to arrive. If that spacecraft encountered an emergency and radioed home for guidance, mission controllers would not receive the distress call for 4 hours. Their response would take another 4 hours to travel back. 8 hours of round-trip communication delay, even at the fastest possible speed. For all practical purposes, any spacecraft operating near Neptune is completely alone. This is not a theoretical abstraction. It has been directly experienced by every deep space mission humanity has ever attempted. When NASA's New Horizons spacecraft made its closest approach to Pluto in July of 2015, the entire encounter occurred on autopilot. Mission controllers had uploaded the flyby sequence hours in advance because one-way signal travel time from Earth to Pluto exceeded 4.5 hours. There was no possibility of real-time guidance. No possibility of sending a corrective command during the encounter and having it arrive while the encounter was still happening. New Horizons executed its observations alone, stored the data, and then spent over 15 months slowly transmitting the results back to Earth at a data rate of roughly 1 to 2 kilobits per second. The complete dataset from a flyby that lasted hours took more than a year to download across the solar system's distances, and Pluto is close by the standards of what lies beyond it. Voyager 1, launched by NASA in September of 1977, and traveling continuously ever since at approximately 38,000 miles per hour, has covered roughly 15 billion miles from the Sun. 15 billion miles in nearly 5 decades of uninterrupted travel. The spacecraft has crossed the heliopause, the boundary where the solar wind transitions into the interstellar medium, making it the first human-made object to enter interstellar space. By any measure, Voyager 1 represents the most distant point ever reached by anything humanity has ever built or launched. It is our outermost emissary, our farthest physical extension into the cosmos. And yet, despite traveling for nearly half a century at 38,000 miles per hour, Voyager 1 remains within the Sun's extended gravitational domain. It has not escaped our star's neighborhood. It has barely crossed into the outermost suburbs. At its current velocity, it would require approximately 73,000 years to cover the distance to Proxima Centauri, the nearest star to our Sun. If it were aimed in that direction, which it is not, 73,000 years. That is roughly 9 times the entire span of recorded human civilization, from the earliest clay tablets of Mesopotamia to this moment. The fastest object our species has ever deliberately sent outward from Earth cannot reach the next star over in any time frame that has meaning for nations, languages, cultures, or species. The communications link with Voyager 1 is itself a masterpiece of engineering pushed to its absolute limits. The spacecraft broadcasts its data home using a radio transmitter that operates at roughly 22 watts, approximately the power of a small light bulb, or a moderately efficient laptop computer. That signal spreads outward from the spacecraft in all directions as it crosses the solar system, thinning with distance according to the inverse square law. By the time it reaches the massive dish antennas of NASA's Deep Space Network on Earth, the received power measures roughly 10 to the negative 17 watts. That is 100 billion times weaker than a standard wristwatch battery. NASA engineers must use cryogenically cooled receivers, chilled nearly to absolute zero, to reduce the thermal noise that would otherwise drown the signal, and average hours of incoming data just to extract coherent information from the electronic noise floor. That degraded, nearly lost whisper from a spacecraft 15 billion miles away is the farthest direct communication humanity has ever managed. It represents the absolute outer boundary of what our technology can hear at this moment, and it is coming from inside our own solar system. Making the emptiness physical, let us make all of this emptiness visceral. Let us build a scale model and walk through it. Imagine shrinking the sun down to the size of a large grapefruit, roughly 8 inches across. At that scale, what does the rest of the solar system look like? Earth becomes a small pebble, less than a quarter-inch in diameter, sitting about 75 feet from where you set the grapefruit down. Mars is a slightly smaller pebble at roughly 115 feet. Jupiter, the giant of the solar system, becomes a sphere about 3 inches across, sitting approximately 390 feet away from you. Saturn, slightly smaller, hovers at around 700 feet. And Neptune, the most distant major planet, would be a ball, roughly the size of a golf ball, sitting nearly half a mile away from that grapefruit. Half a mile. And the Sun in the scale model is an object you can hold in one hand. If you placed it on the 50-yard line of a football stadium, Neptune would be sitting in a field somewhere half a mile outside the stadium parking lot. You would need to leave the game, walk out of the stadium, out of the parking lot, down a road for several minutes, and keep walking before you found Neptune. And the vast majority of the space between every point in that walk would be completely, entirely empty. No objects, no structures, no material of any kind, just vacuum. But it is the next step in the model that reveals the true character of the universe. At this same scale, where the Sun is a grapefruit on the 50-yard line, where Earth is a pebble at 75 feet and Neptune is half a mile away, the nearest neighboring star system, Proxima Centauri, would be located approximately 4,000 miles away. 4,000 miles. Imagine standing at that 50-yard line in a stadium in New York City. At this scale, Proxima Centauri, the closest star to our Sun, would be sitting somewhere in the middle of the Pacific Ocean, roughly halfway to Japan. You could drive across the entire continental United States, keep driving, board a ship, cross most of the Pacific Ocean, and still not reach the nearest neighboring star. That is the gap between suns in our part of the galaxy. The space between stars does not merely exceed the space between planets. It belongs to an entirely different category of distance. It makes the solar system, which already defeated our intuitions so comprehensively, look like the distance between pieces of furniture in a room. And that interstellar space is not merely empty. It is actively hostile in ways that scale with your speed through it. The interstellar medium, the material that fills the space between stars in our region of the Milky Way, contains on average roughly 1 atom per cubic centimeter. 1 atom. For reference, the air in your living room contains approximately 25 billion molecules per cubic centimeter. The interstellar medium is so incomprehensibly sparse that calling it matter requires charitable interpretation of the term. But for a spacecraft traveling at any significant fraction of the speed of light, this near-nothingness transforms into a serious physical hazard. At 10% of the speed of light, approximately 67 million miles per hour, each individual hydrogen atom encountered by a spacecraft would strike the hull with the energy of a particle accelerator. Collision. Over the course of a 4-light-year journey to Proxima Centauri, the cumulative bombardment from trillions of these impacts would deliver enough radiation to erode shielding materials and potentially destroy sensitive instruments. Microscopic dust grains in the interstellar medium, each one carrying kinetic energy equivalent to a small explosive charge at those relative velocities, would pepper any approaching craft with forces that dwarf any engineering margin we currently designed for. The void between stars is not a passive emptiness waiting peacefully to be crossed. It is a thin, invisible gauntlet that grows more lethal with every increment of speed you apply to crossing it. And these interstellar voids are simply the gaps between individual houses in a city of 400 billion houses. A grain of rice on a football field? All of this, the planets, the sun, the Voyager spacecraft, the 15 billion miles of distance traversed over nearly 5 decades. The interstellar medium and its microscopic hazards exists inside a single galaxy, the Milky Way. A structure so vast that the entire solar system, with all its planets and moons and comets and billions of miles of empty space, would not register as a single visible dot in a photograph taken from outside it. Here is the comparison that will hollow out your sense of scale if you let it land properly. If you placed a single grain of rice at the 50-yard line of an American football field and declared that grain to represent the entire solar system, all of it, every planet, every moon, every comet, every spacecraft, everything, the football field itself would not even begin to represent the Milky Way. At that scale, our galaxy would extend far beyond the stadium, beyond the parking lot, beyond the surrounding neighborhoods, beyond the city, beyond the metropolitan area. The grain of rice sitting on the field, representing everything we have ever directly explored, would be invisible to anyone sitting in the stands. You could walk down to the 50-yard line, kneel on the turf, and search with a magnifying glass, and you would struggle to find it. Everything. Every signal humanity has ever broadcast into space. Every trajectory calculated for every spacecraft ever launched. Every star visible to the naked eye from Earth. Every constellation ever named. All of it fits inside an object smaller than a grain of rice, sitting in the middle of a football field, that is itself a vanishingly small fraction of the galaxy it's meant to represent. The Milky Way is a barred spiral galaxy. Seen from a sufficient distance above, it would resemble a vast, slowly rotating pinwheel curved arms of stars, gas, and dust spiraling outward from a dense central bar of older reddish stars. The disk of visible stars measures approximately 100,000 light-years in diameter. To cross it at the speed of light, the absolute maximum velocity permitted by physics would take 100,000 years. A beam of light departing one edge of the Milky Way at this exact moment would not reach the opposite edge until roughly 100,000 years after every trace of human civilization had crumbled and been forgotten, and had crumbled again and been forgotten again many times over. That is the width of the galaxy we live in. 100,000 light-years of stars, gas, dust, dark matter, stellar nurseries, supernova remnants, neutron stars, black holes, and vast stretches of near-perfect interstellar vacuum, all gravitationally organized into a single rotating structure. The disk is relatively thin, compared to its width roughly 2,000 light-years thick in the region near our Sun, giving it the rough proportions of a dinner plate. But even that 2,000 light-year thickness means that light needs 2 full millennia to travel from the top of the galactic disk to the bottom in our neighborhood. 2,000 years of travel at the maximum speed of the universe just to cross the thin edge. Within this disk, The Milky Way contains somewhere between 200 billion and 400 billion individual stars. The exact number remains uncertain because our position inside the galaxy, buried within the disk itself and surrounded by thick clouds of interstellar dust, limits our ability to count stars on the far side. Infrared observatories have pushed our estimates further than optical telescopes ever could, but a precise census of every star in the Milky Way remains beyond current capability. What is not in doubt is the general magnitude. If you attempted to count every star in our galaxy at a rate of 1 per second, never pausing, never sleeping, never resting, the task would take you somewhere between 6,300 and 12,700 years. You would need to have started counting before the construction of the Egyptian pyramids, and continue uninterrupted past the present day and thousands of years into the future before you finished. Each of those hundreds of billions of stars is a sun. Some are monstrous, dwarfing our own in every dimension. Blue supergiant stars like Rigel burn with luminosities exceeding 100,000 times the sun's energy output. Red hypergean stars like UY Scuti have diameters so vast that if placed at the center of our solar system, their surfaces would extend beyond the orbit of Jupiter, swallowing every inner planet, every asteroid in the belt, and consuming the volume in which Earth orbits. Other stars are inconceivably small and feeble. Red dwarf stars, which make up roughly 70% of all stars in the Milky Way, burn with such negligible luminosity that not a single one is visible to the naked eye from Earth. Despite being by far the most common type of star in our galaxy, our sun falls comfortably in the middle of this enormous range. Brighter than most stars, dimmer than many, larger than some, smaller than others. In a galaxy of hundreds of billions of stars, our star is thoroughly, unremarkably average. The suburbs of the galaxy. Our solar system sits approximately 26,000 light-years from the galactic center, not near the dense, blazing core, where stars are packed thousands of times more tightly than in our neighborhood. Not at the sparse outer rim, where stellar density thins toward almost nothing. We are embedded in a modest, unremarkable region of the disk, roughly halfway between the center and the edge, situated in a minor spur of stars that branches off between two of the galaxy's major spiral arms. Astronomers call this the Orion Spur. In galactic terms, we live in the suburbs, a middling neighborhood in a middling galaxy. That is, as we are about to discover, middling among its immediate cosmic neighbors. The Sun and everything gravitationally bound to it orbits the galactic center at a speed of approximately 515,000 miles per hour. Despite this extraordinary velocity, the sheer circumference of the orbit means that one complete circuit takes roughly 230 million years. This is sometimes called a galactic year. In the 4.5 billion years since the solar system coalesced from a cloud of gas and dust, our star has completed approximately 19 or 20 full orbits of the Milky Way center. The last time our sun occupied this exact position in the galaxy, 230 million years ago, Earth was in the early Triassic period. Dinosaurs were just beginning to appear. The supercontinent Pangaea was still largely intact, a single vast landmass beginning its slow tectonic fracture. No grass existed anywhere on the planet because grasses had not yet evolved. No flowers, no birds, no small mammals beyond the earliest, most primitive forms. The world was populated with strange, unfamiliar creatures. Archosaurs, therapsids, early synapsids, that would be unrecognizable to modern eyes in every important sense. That is how long a single galactic orbit takes, and the Sun has completed it fewer than 20 times in its entire existence. To understand how invisible our solar system is within this structure, consider one final comparison. If you stood at the center of the Milky Way and looked outward toward our Sun, trying to locate it specifically among the stars of the galactic disk, the task would be functionally equivalent to standing in the center of a completely darkened Manhattan at midnight and trying to identify one specific firefly hovering somewhere among 400 billion other fireflies scattered across the city. Every firefly is glowing. Every firefly is moving on its own trajectory. And the one you are looking for is perfectly average in brightness, perfectly average in size, located in a section of the city with no distinguishing characteristics whatsoever. You would not find it in a human lifetime. You would not find it in 1,000 human lifetimes. We are invisible within the galaxy we inhabit. When you look up on a clear, dark night and see the pale, milky band of light arching across the sky, that river of soft luminosity that ancient peoples named with their own mythologies, you are seeing the combined glow of billions of distant stars in the galactic disk, too far away to be resolved individually by the naked eye, blending into a continuous, luminous river that represents the edge-on view of the structure we call home. That river is the Milky Way. It is the largest structure that most people will ever pause to contemplate. And it is not the largest thing in our immediate cosmic neighborhood, not even remotely close. The smudge that shattered the universe. On a clear autumn night in the northern hemisphere, if you know where to look in the constellation Andromeda, you can find a faint smudge of light hanging in the sky. It appears dim, slightly fuzzy at the edges, easily dismissed as a flaw in your vision or a thin cloud across the stars. Ancient astronomers cataloged it dutifully as a nebula, a cloud of glowing gas somewhere within the confines of what they believed to be the entire universe. For centuries, even as telescopes improved, and the smudge resolved into something with more internal structure, that assumption held. This was local. This was ours. The idea that this gentle blur of light could be something grander, an entirely separate system of stars, at an almost incomprehensible remove from anything in our own galaxy, did not enter serious scientific discussion until the early 20th century. And when the truth finally emerged, it did not merely expand the known universe. It shattered the entire existing framework for understanding the cosmos and revealed a reality so much larger than anyone had dared to propose that the announcement was initially met with disbelief. The story of that discovery deserves to be told properly, because it is one of the most consequential single moments in the history of human knowledge. In the early 1920s, the astronomical community was locked in what became known, with characteristic scientific understatement, as the Great Debate. On one side stood astronomers who believed the Milky Way constituted the entire universe in its totality, with all the spiral and elliptical nebulae visible through telescopes being merely clouds of gas and dust within our own galaxy's borders. On the other side stood those who argued, based on the distances implied by their brightness and the nature of their internal structure, that these nebulae were island universes' entire independent galaxies, comparable in scale to the Milky Way, located at vast, almost unimaginable distances beyond our own galaxy's edge. Neither side had definitive evidence. The debate was contentious, consequential, and unresolved. Edwin Hubble settled it on a cold night in California in the early 1920s, working with the 100-inch Hooker telescope at Mount Wilson Observatory, at the time the largest operational telescope on Earth. Hubble spent months painstakingly exposing photographic plates aimed at the Andromeda Nebula, pushing the instrument to the limits of its sensitivity in an attempt to resolve individual stars within the smudge that lesser telescopes had seen only as a uniform glow. The Hooker's unprecedented light-gathering capability allowed him to do what no previous instrument could. He separated the diffuse blur into discrete, individual points of light. Among those resolved stars, Hubble identified something critical, a Cepheid variable, a type of star whose brightness pulsates in a regular, reliable cycle, brightening and dimming with a period determined by its own intrinsic luminosity. The key to using Cepheids as cosmic measuring tools had been established years earlier by astronomer Henrietta Swan Leavitt, who had discovered through painstaking analysis of stars in the Magellanic Clouds that the pulsation period of a Cepheid is directly and predictably correlated with its true intrinsic brightness. A Cepheid that pulsates over a longer period is genuinely more luminous, not merely appears brighter because it is closer, but is actually producing more energy. This period luminosity relationship gave astronomers their first reliable cosmic yardstick, a way to determine the true brightness of a distant star simply by watching it blink. Hubble measured the pulsation period of the Cepheid he had found in Andromeda. The period told him its true luminosity. Comparing that known true luminosity to the star's faint apparent brightness as observed from Earth allowed him to calculate the distance, using the simple physical law that governs how light dims with distance. When he completed the calculation, the result was staggering. The star, and therefore the nebula containing it, was located approximately 900,000 light-years from Earth. A figure later revised upward significantly as measurement techniques improved. until the modern accepted value settled at approximately 2.5 million light-years. 900,000 light-years, even by the original estimate, was far beyond the then-current estimates of the Milky Way's maximum extent. The Andromeda Nebula was not a gas cloud within our galaxy. It was a galaxy in its own right, a separate, independent system of stars at a distance so enormous that it placed it entirely outside anything previously conceived as part of the universe. In a single calculation from a pulsating star on a photographic plate, the known universe expanded from one galaxy to at least two. The great debate was over. Not gradually, not through a slow accumulation of converging evidence. It was resolved on a single night, by a single measurement, using a technique developed by a woman whose contribution would go largely uncredited for decades. And the universe that emerged from that measurement was incomprehensibly, almost insultingly larger than the one that had preceded it. That faint smudge you can find with your naked eye, the one ancient astronomers cataloged as a local cloud, is the Andromeda Galaxy, formerly designated Messier 31, or M31, in astronomical catalogs. It is the most distant object visible to the unaided human eye, and what you are looking at, when you find it, is the combined light of approximately 1 trillion individual stars. 1 trillion. Not 1 billion. 1 trillion. A number so large that if you attempted to count them at 1 per second, the task would take roughly 31,000 years. The Milky Way, our home galaxy, contains between 200 billion and 400 billion stars. Andromeda harbors roughly 1 trillion. Depending on which current estimate you use for our own galaxy's stellar population, Andromeda contains between 2.5 to 5 times as many stars as the Milky Way. Every sun that powers every planet that harbors any possibility of life within our entire galaxy could be multiplied several times over and still not match the stellar population of the galaxy sitting next door. When you look at that faint smudge on a clear autumn night and your retina catches a photon from it, you are connecting to a system containing more individual nuclear furnaces than the total stellar content of the galaxy you live in. That single act, looking up at a smudge, bridges 1 trillion burning stars. Andromeda, the giant next door. Andromeda's disk stretches across approximately 220,000 light-years. The Milky Way's disk spans roughly 100,000 light-years. If you placed both galaxies side by side in a diagram scaled to their actual relative sizes, Andromeda would dwarf our galaxy the way a beach ball dwarfs a tennis ball. More than double the diameter means 4 to 5 times the surface area. Andromeda is not simply a larger version of our galaxy. It is a categorically larger structure. A galactic giant that makes our home look like a smaller, somewhat overlooked companion, rather than an equal neighbor. The structural differences go beyond raw size. Andromeda is also a spiral galaxy, but its spiral arms are more tightly wound than the Milky Way's, and its central bulge, the dense concentration of older, redder stars surrounding the galactic core, is significantly more prominent. While the Milky Way's central region is shaped into an elongated bar, Andromeda's bulge is rounder, more massive, and more visually dominant. The size and prominence of a galaxy's central bulge tells astronomers something important about its history. Larger, more prominent bulges typically indicate a more extensive merger history, more past interactions and absorptions of other galaxies over cosmic time. Andromeda's prominent central bulge suggests it has consumed more satellite galaxies over its lifetime than the Milky Way has, growing its central regions through repeated gravitational cannibalism across billions of years. Both galaxies harbor supermassive black holes at their centers. In the Milky Way, our central black hole, known as Sagittarius A, weighs approximately 4 million times the mass of our Sun. 4 million solar masses is an extraordinary concentration of matter, but Andromeda's central black hole dwarfs it. Weighing in at approximately 100 million solar masses, it is roughly 25 times heavier than the object sitting at the center of our own galaxy. If Sagittarius A is a boulder at the Milky Way's center, Andromeda's black hole is a mountain range. This mass differential reflects the difference in each galaxy's feeding history. Andromeda's core has consumed far more material over cosmic time. Andromeda's globular cluster population tells the same story of comparative dominance. Globular clusters ancient, densely packed spheres of hundreds of thousands to millions of stars, some dating back to within a billion years of the Big Bang itself. Number approximately 150 known examples in the Milky Way. Andromeda possesses roughly 450. 3 times as many of these ancient stellar relics orbit Andromeda's center, each one a gravitational relic of the early universe, testament to Andromeda's larger gravitational sphere of influence and more extensive history of satellite galaxy absorption. Andromeda also commands a larger gravitational entourage. It has at least 35 confirmed satellite galaxies orbiting it, and likely harbors more awaiting discovery. Its most prominent companions, M32 and M110, they are themselves being slowly dismantled by Andromeda's gravity, their outer stellar populations progressively stripped away and scattered into Andromeda's halo through tidal interactions playing out over hundreds of millions of years. M32 in particular shows signs of being a former mid-sized spiral galaxy that has been stripped down to its dense core by billions of years of close orbital proximity to Andromeda. Andromeda is not merely a large galaxy. It is an active gravitational predator, consuming its smaller neighbors more aggressively than our own galaxy currently does. Both of these galaxies, this gravitational giant and its somewhat smaller but still enormous companion, belong to the same cosmic neighborhood. Astronomers call it the local group. This gravitational family contains more than 80 individual galaxies, though the vast majority are small dwarf galaxies containing only a few billion stars or fewer. The local group spans roughly 10 million light-years across, with the Milky Way and Andromeda acting as the 2 dominant gravitational anchors around which everything else slowly orbits. The third largest member, the Triangulum galaxy, contains approximately 40 billion stars, a respectable number on its own terms, but dwarfed by both of its larger neighbors. The smaller dwarf galaxies orbit either the Milky Way or Andromeda as moons orbit planets, slowly being drawn inward by their host galaxy's gravity, many of them destined to be torn apart and absorbed. Within this local group, the Milky Way and Andromeda dominate everything. Together, they account for the overwhelming majority of the group's total mass and stellar population. They are the gravitational anchors of this particular corner of the cosmos, and they are not sitting still. 2.5 million light-years. Closing. The Milky Way and Andromeda are separated by approximately 2.5 million light-years of intergalactic space. That distance represents a gulf so vast that light itself, traveling at the universe's absolute speed limit, requires 2.5 million years to cross it. The photons arriving at your eyes from Andromeda tonight left that galaxy before the genus Homo existed, before any human ancestor had yet evolved the brain size, the upright posture, the hand anatomy, or the social complexity that we now think of as distinctly human. That light was already ancient when the first recognizably human creatures walked the African savanna. It was already ancient when the last common ancestor of humans and chimpanzees lived. It was making its 2.5 million year crossing through the intergalactic void, while entire evolutionary lineages rose and fell on a small planet it was sailing toward, without any knowledge of its destination. And now, it ends its journey on the surface of your eye. The intergalactic space between the Milky Way and Andromeda is not perfectly empty. Scientists have detected extremely tenuous distributions of matter in this region. Hot ionized gas, primarily hydrogen and helium, at temperatures reaching hundreds of thousands of degrees. Dark matter filaments thread through the void as remnants of the large-scale cosmic web that connects galaxies across the universe. Occasionally, a stray star ejected from one galaxy or the other drifts through this space, unbound to any galactic structure, traveling alone through the darkness at hundreds of thousands of miles per hour with no destination and no company. But the density of this material is so extraordinarily low that calling it matter requires the most charitable possible interpretation of the word. The average density of intergalactic space in the region between the Milky Way and Andromeda is roughly 1 atom per cubic meter. 1 atom. In a volume of space the size of a large refrigerator box, you would find, on average, a single hydrogen atom. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. The difference in density between the air in your lungs and the intergalactic medium between here and Andromeda spans a factor of roughly 10 to the 25th power, a number so large that it ceases to function as an antromedium, intuitive comparison, and begins to function as direct evidence that the universe was not constructed to accommodate human comprehension. Intergalactic space is emptier than anything that can be manufactured on Earth. The most advanced vacuum systems ever built by human engineers, the ultra-high vacuum chambers used in particle accelerators and precision experiments, still contain millions of molecules per cubic centimeter. The natural vacuum of intergalactic space between here and Andromeda is more perfect than anything our civilization has yet built. This is the space that separates us from the nearest giant galaxy. 2.5 million light-years of near-perfect nothingness. No waypoints, no landmarks, no gravitationally significant structures to navigate by, no sources of fuel or energy along the route, no raw materials for construction or repair, no electromagnetic signals strong enough to serve as beacons, just a vast, featureless, effectively empty gulf stretching for 14.7 quadrillion miles between two islands of organized matter that are, relative to the distance between them, vanishingly small. And across this void, something is happening. Andromeda is moving toward us. This is not theoretical. It is observationally confirmed and has been for more than a century. The evidence comes from spectroscopic analysis of Andromeda's light. When an object moves toward an observer, the wavelengths of light it emits are compressed slightly shifted toward the blue end of the electromagnetic spectrum. This blue shift is the light wave equivalent of the rising pitch of a siren approaching from down the street. Andromeda's light is blue shifted. The galaxy is approaching. This was first measured by astronomer Vesto Slipher in 1912 at Lowell Observatory in Flagstaff, Arizona, making Andromeda one of the first galaxies ever measured to have a significant velocity relative to our own. The measurement has been confirmed and refined continuously in the century since by multiple independent instruments and techniques. The current best estimate for Andromeda's approach, velocity along the direct line between the two galaxies, is approximately 110 kilometers per second, translating to roughly 250,000 miles per second, hour. At that speed, the distance between the two galaxies shrinks by about 110 kilometers every single second. Over the course of one Earth year, Andromeda moves approximately 3.5 billion kilometers closer to us. Every year, a distance equivalent to nearly the full span between the Sun and Uranus is erased from the intergalactic gap. That sounds fast, and in terrestrial terms, it is. 250,000 miles per hour is fast enough to cross the distance between Earth and the Moon in approximately 1 hour. But against the scale of intergalactic space, it is glacially, almost heartbreakingly slow. At this approach speed, the full closing of the 2.5 million light-year gap would take roughly 4 to 5 billion years. That is approximately the same amount of time Earth has already existed. The journey that Andromeda is making toward us has been underway for billions of years already, and it will continue for billions more. You will never notice it. Your civilization will never notice it. The entire lifespan of human existence on this planet, from the first members of our species to whatever conclusion we eventually reach, will not be long enough to detect any measurable change in Andromeda's position through naked eye observation. What comes next is the story of what happens when these two enormous structures finally meet. The science of the collision. More complicated than you've been told. For decades, the standard description of the Milky Way-Andromeda interaction has been presented with the clean confidence of settled science. Two galaxies on a collision course. A head-on impact in approximately 4 to 4.5 billion years. The resulting merger produces a single, massive, elliptical galaxy. This version of the story has appeared in documentaries, textbooks, planetarium shows, and popular science articles, so consistently and for so long that most people who follow astronomy at all treat it as established, unambiguous fact. It has the satisfying narrative simplicity of a billiard ball problem. Two objects, one trajectory, one outcome. But the full picture is considerably more nuanced. The scientific community's understanding of this interaction has evolved significantly over the last decade. And what has emerged from that evolution is a story that is both more uncertain in its specific details and more fascinating in its complexity than the simplified version suggests. Here is the distinction that matters. Andromeda's radial velocity, the speed at which it approaches us directly along the line connecting the two galaxies, is well measured and has been confirmed repeatedly, approximately 110 kilometers per second. This number is solid, but radial velocity tells you only one component of motion. It tells you how fast the gap is closing along one specific axis. It tells you nothing about how Andromeda is moving sideways relative to that line. This sideways component, the transverse velocity, is critical for predicting the actual geometry of the encounter. Whether the two galaxies will meet in a direct head-on collision, execute a glancing blow that sets up a later merger, or even pass each other partially on the first approach before gravity pulls them back for a second pass, depends almost entirely on the transverse velocity. And for most of the history of this discussion, that transverse velocity was essentially unconstrained by observation. Measuring the sideways drift of a galaxy sitting 2.5 million light-years away requires detecting an angular shift in its position on the sky so tiny accumulated over observation periods of years that it strains the limits of what astronomical instruments can do. Most early models simply assumed the transverse velocity was small and treated a head-on collision as the most probable scenario. It was not a bad assumption given the available data, but it was still an assumption. That changed with the European Space Agency's Gaia spacecraft. Gaia was designed to measure the precise positions and proper motions of stars across the sky with unprecedented accuracy, tracking angular shifts smaller than a millionth of a degree. By monitoring the average motion of stars within Andromeda relative to distant background quasars that serve as fixed reference points in the sky, researchers were able to extract the first genuinely robust measurements of Andromeda's transverse velocity. What they found complicated the simple collision narrative considerably. Studies published using Gaia data, most notably a 2019 analysis based on the Gaia data release, estimated Andromeda's transverse velocity at approximately 57 kilometers per second, with measurement uncertainties allowing values ranging from roughly 40 to 70 kilometers per second. This is not a negligible sideways motion. A significant transverse component means the two galaxies are not approaching each other in a straight line. They are on a path that includes a meaningful sideways offset, and that offset has real consequences for the predicted encounter. A higher transverse velocity makes a perfectly direct head-on collision on the first pass less likely. Instead, the galaxies may execute an initial flyby passing close enough for their dark matter halos and outer stellar populations to interact gravitationally, generating tidal distortions and triggering some early star formation, but without the immediate full merger that earlier, simpler models predicted. After the first close approach, the gravitational attraction between the two systems would gradually drain orbital energy from the interaction, a process called dynamical friction, slowing their relative motion and pulling them back toward each other. A second approach would follow, likely closer and slower, then another and another, each pass drawing the galaxies into deeper gravitational entanglement until they eventually coalesce into a single system. This revised scenario does not eliminate the merger. It postpones and complicates it. The two galaxies are gravitationally bound to each other beyond any reasonable doubt. Their mutual attraction is stronger than the cosmological expansion that carries most galaxies apart. Some form of significant interaction will occur. The radial blue shift is confirmed. The gravitational binding is real. What remains under active investigation is the precise choreography. Whether the first pass is head, on, or glancing, how many orbits precede full coalescence, and exactly how far into the future the final merger lies. Some current models place the first close encounter at roughly 4.5 billion years from now, with the full merger completing somewhere between 8 and 10 billion years in the future, rather than the 4 to 5 billion years of older estimates. The timeline is stretched. The story has become more complicated. Anyone who presents the Milky Way-Andromeda collision as a simple, precisely predicted event with a fixed calendar date is oversimplifying a problem that the scientific community is still actively working to constrain. What is not oversimplified is this. The collision is coming. The merger, over whatever timeline the orbital mechanics ultimately dictate, is effectively certain. And when it happens, it will be one of the most consequential events in the future history of this corner of the universe, even if not a single living thing will be present to observe more than a fraction of it in anything resembling real time. What a galactic merger actually looks like. The popular imagination, when confronted with the idea of two galaxies colliding, tends to generate images of spectacular, catastrophic destruction. Fireballs consuming entire star systems, planets torn from their orbits, stars crashing into each other in cascades of nuclear fire. A cosmic wreck of almost incomprehensible violence. This image is almost entirely wrong. Understanding why requires returning to the fundamental lesson this entire journey has been building toward, the lesson about emptiness. Stars within galaxies are separated by distances so vast relative to their own sizes that the probability of any two stars physically colliding during a galactic merger is vanishingly, statistically negligible. In the region of the Milky Way surrounding our Sun, the average distance between neighboring stars is roughly 4 to 5 light-years. Each star is at most a few million miles across. The gaps between them span trillions of miles. The ratio of empty space to stellar material is so extreme that galaxies are, in the most physically honest sense of the word, almost entirely made of nothing. Here's the comparison that makes this concrete. If you shrank our Sun to the size of a bowling ball and placed it in the center of a large cathedral, the nearest neighboring star at the same scale would be a second bowling ball, sitting in a different cathedral, in a completely different city, hundreds of miles away. Between those two bowling balls, at this scale, representing the actual density of stars in our neighborhood, there would be absolutely nothing. No other objects of any meaningful size. Just the vast, empty interior of a continent-scale space, punctuated here and there by tiny sub-bowling ball objects representing planets. This is the actual density of matter in a galaxy. And it means that when two galaxies pass through or near each other, the individual stars within them move through each other's galactic space as if the other galaxy were barely there. They are not dense enough for direct stellar collisions to be anything other than a catastrophic statistical rarity. You could run the entire gravitational simulation of the Milky Way Andromeda merger billions of times, with every star's trajectory tracked individually, and direct physical contact between individual stars would remain an extraordinary exception rather than any kind of rule. The merger is not a collision in any sense that a human being would recognize from experience. It is a gravitational event. What does happen, however, is gravitationally dramatic in ways that operate across scales far too large for direct stellar impacts, but are nonetheless transformative in their effects. When two galaxies approach and begin to interpenetrate, the gravitational forces involved are immense. These tidal forces, the differential pull of gravity across the extended structure of each galaxy, do not need to bring individual stars into physical contact to reshape both galaxies profoundly and permanently. Tidal forces warp orbits. They stretch the outer regions of each galaxy's disk into long, curved streamers of stars pulled toward the approaching mass of the other galaxy. They fling stars onto entirely new trajectories, some sent on wide-looping paths that carry them far out into intergalactic space before gravity curves them back, others pull deep into the combined gravitational well, forming at the center of the interaction. The organized, elegant spiral structures that characterize both the Milky Way and Andromeda, the graceful arms that took billions of years of differential rotation to develop, would be progressively distorted, twisted, and eventually destroyed by these tidal forces. Over hundreds of millions of years following the first close encounter, those spiral arms would dissolve into chaotic streams and curving shells of stars. The orderly disk geometry would break down into a less organized, more three-dimensional distribution of stellar orbits. Meanwhile, the gas within both galaxies, the raw material from which stars form, responds very differently from the stars themselves. Stars, being compact and widely separated, pass through each other's galactic space with minimal direct interaction. Gas clouds, being extended and diffuse, behave differently. When the gas from two galaxies meets during a merger, it collides, compresses, and heats up. This compression acts as a trigger. It initiates enormous waves of new star formation regions of both galaxies that had been quiescent for billions of years, suddenly igniting with the birth of millions of new stars in concentrated bursts of activity. These starburst events light up in infrared and ultraviolet radiation, dramatically increasing the combined galaxy's total luminosity during the most active phases of the interaction. Astronomers do not have to model this from first principles alone. They can observe it directly, happening right now, in other galaxy pairs across the observable universe. The Antennae galaxies, two spiral galaxies currently colliding approximately 63 million light-years from Earth, provide one of the most studied examples of an ongoing galactic merger. Their images show spectacular plumes of material pulled outward by tidal forces into long curving tails, and their overlap regions blaze with newly triggered star formation exactly as models predict. These two galaxies began their interaction hundreds of millions of years ago and are now deeply entangled, their structures so thoroughly interpenetrated that the individual identities of each original galaxy are becoming difficult to disentangle. The Mice galaxies, NGC 4676, a pair of interacting spirals roughly 300 million light-years away, show an earlier stage. Two distinct spiral disks still largely intact, but already connected by long tidal tails of stars and gas streaming outward between them, like slow-motion debris trails from a gravitational accident. The tails have been pulled out to lengths of hundreds of thousands of light-years, longer than the diameter of our entire galaxy by the tidal forces of the interaction. The Cartwheel galaxy, roughly 500 million light-years away, captures an even rarer geometry. It is a ring galaxy formed when a smaller galaxy passed directly through the center of a larger spiral disk, sending a concentric shockwave of compressed gas and triggered star formation expanding outward from the impact point in a ring, like a ripple spreading across the surface of a pond after a stone is dropped. The smaller intruding galaxy has already passed through and moved away from the larger one, and the resulting ring structure of new stars and ionized gas, still expanding outward from the point of penetration, is unlike anything found naturally in the local group. These are not simulations. They are real galaxies, observed at various stages of gravitational interaction, providing a visual catalog of what the Milky Way Andromeda encounter will resemble across different phases of the event. Astronomers study these systems as proxies for our own galaxy's future, using their measured properties to calibrate and validate the computer models that project the eventual merger forward in time. The starburst phase triggered by the gas collision would be spectacular in terms of energy output, but relatively brief in cosmic terms. Within a few hundred million years of the initial gas collision, the easily compressible fuel would either be converted into newly formed stars, heated to temperatures too high for further gravitational collapse, or expelled from the merger region by the fierce radiation and stellar winds from the newly formed massive stars and from any active galactic nuclei, triggered by gas flowing toward the merging central black holes. After the starburst, star formation would decline sharply as the available cold gas was depleted. The end state, reached perhaps 1 to 2 billion years after the final coalescence of the two galactic cores, would be a massive elliptical galaxy. No spiral arms, no rotating disk, no organized structure of the kind that currently defines both the Milky Way and Andromeda. Just a roughly spherical or slightly elongated concentration of hundreds of billions of stars, orbiting a common center of mass in randomized directions. The orbits shuffled and reshuffled by the gravitational chaos of the merger, until all memory of the original disk geometry has been erased. Astronomers have proposed several informal names for this future merged structure. Milkdromeda is the most commonly cited. The name is lighthearted. The reality it describes would be anything but small. A combined system containing somewhere between 1.5 and 2 trillion stars, with a combined mass potentially exceeding 2 trillion times the mass of our Sun, dominated by 1 or 2 supermassive black holes that would themselves eventually spiral together and merge in an event producing gravitational waves potentially detectable across the observable universe. What about our solar system during this process? If the Sun still exists at the time of the first close encounter, which depends on the precise timeline, since the Sun's main sequence, lifetime ends in roughly 5 billion years, and the merger timeline may extend beyond that. The most likely outcome for any surviving star systems is not destruction, but displacement. The stars of both galaxies are so widely separated that direct stellar collisions will remain negligible throughout the entire merger, as we have established. The sun would not be destroyed by another star crashing into it. But gravitational perturbations during the chaotic redistribution of orbits could substantially alter the sun's trajectory within the merged galaxy. It might be flung outward into the halo of the new combined system, orbiting at a much greater distance from the galactic center than it currently does. It might be pulled inward toward the core. In some simulated merger scenarios, a fraction of stars are ejected entirely from the merged system, flung into intergalactic space at high velocity as unbound rogues drifting through the void with no galactic home. From the perspective of any inhabitants on a planet orbiting a surviving star caught in this merger, the changes would be imperceptible on human timescales. A galactic merger unfolds over hundreds of millions of years. The night sky would change gradually across millennia, then across millions of years. Stars from Andromeda would appear in constellations that slowly, over generations beyond counting, distorted beyond recognition. The band of the Milky Way across the sky would warp, brighten in some regions, thin in others, and eventually dissolve into a more diffuse and uniform glow as the disk structure was destroyed. New nebulae would ignite across regions of fresh star formation. But none of this would happen fast enough for any individual observer or any civilization persisting for a few thousand years to see it change. A galactic merger is an event measured in geological time multiplied by a factor of thousands. It would be like watching a mountain erode. The process is real, powerful, and ultimately total in its transformative effect, but you would never see it move. The arithmetic of impossibility. We have now measured everything within reach of current astronomy. We know the size of the Earth. We know the size of the Sun. We know the distances between planets and the character of the emptiness that fills the solar system. We know the scale of the Milky Way, with its hundreds of billions of stars spread across 100,000 light-years of space. We know the dimensions of the Andromeda galaxy more than twice the diameter of our home, containing up to 1 trillion stars, with a central black hole 25 times more massive than ours, approaching us at 250,000 miles per hour, across 2.5 million light-years of near-perfect vacuum. All of these are confirmed, measured, published, verified facts. The numbers are real. The distances are real. The physics is real. Now comes the part of the story that no amount of technological optimism or engineering ambition can soften, because now we ask the question that every measurement in this journey has been quietly building toward. Could we ever cross that distance? Could any civilization, using any technology governed by any form of known biology, travel from the Milky Way to the Andromeda galaxy within a time frame that means anything at all to the beings who attempt it? The answer comes not from pessimism, but from arithmetic. And arithmetic, unlike optimism, does not negotiate. Let us start with what humanity has actually built and launched. The fastest object our species has ever sent into deep space on an outbound trajectory is Voyager 1, traveling at approximately 38,000 miles per hour relative to the Sun. At that velocity, Voyager 1 covers roughly 333 million miles per year. That sounds, at first hearing, like rapid progress. It is faster than any car, any aircraft, any conventional rocket engine that has ever carried a human being. It represents the upper edge of what mid-20th century propulsion technology was able to achieve in a sustained, outbound trajectory. At 38,000 miles per hour, traveling continuously without deceleration, without interruption, without any obstacle or gravitational interference, Voyager 1 would require approximately 44 billion years to reach the Andromeda galaxy. 44 billion years. Let that number be stated clearly, without softening. The current age of the universe measured from the Big Bang to this exact moment is approximately 13.8 billion years. The journey to Andromeda at Voyager's speed would take more than 3 times the entire age of the universe. The universe itself has not existed long enough for our fastest outbound spacecraft to complete this trip. If Voyager 1 had been launched at the precise moment of the Big Bang, traveling through the infant cosmos before galaxies or stars or planets had yet formed, it would still not have arrived at Andromeda by now. It would still have approximately 30 billion years of travel remaining, more than twice the current age of the universe still ahead of it. That is the chasm between human engineering and intergalactic distance. Not a gap measured in decades or centuries, of incremental progress, not a challenge awaiting the next generation of rocket engines. A gap that exists at a fundamentally different order of magnitude from anything our species has ever confronted. New Horizons. The spacecraft that flew past Pluto in 2015 and provided humanity's first close-up images of that distant world achieved a launch velocity of roughly 36,000 miles per hour, marginally slower than Voyager. The difference between these two speeds is so cosmically irrelevant to the problem of reaching Andromeda that choosing between them is analogous to choosing between two different walking paces for a journey from a room in New York to the surface of Mars. Both paces are correct. Neither pace matters. The distance makes both choices identical in their inadequacy. What about the Parker Solar Probe? Currently the fastest human-made object relative to the Sun. During its closest solar approaches, the Parker Solar Probe achieved speeds of approximately 430,000 miles per hour, more than 11 times faster than Voyager 1. And genuinely, a remarkable engineering achievement, representing a real leap in achievable velocity. At 430,000 miles per hour, reaching Andromeda would take approximately 3.9 billion years. 3.9 billion. The Earth is 4.5 billion years old. The fastest object humanity has ever constructed would need a travel time roughly comparable to the entire age of our planet to reach the galaxy next door. The entire history of complex multicellular life on Earth, from the Cambrian explosion roughly 540 million years ago to the present day, fits comfortably inside the remaining travel time after the first billion years of the Parker Solar Probe's theoretical Andromeda journey. Its velocity, which would flatten any material object on Earth on contact, which exceeds the escape velocity of every planet in our solar system, which represents the current absolute pinnacle of human propulsive achievement, buys us almost nothing against intergalactic distance. It reduces the travel time from completely absurd to marginally, imperceptibly less absurd. But these are existing technologies. Let us consider theoretical ones. Propulsion concepts grounded in real physics, discussed in peer-reviewed engineering literature, that do not yet exist but are not prohibited by known physical laws. The Breakthrough Starshot Initiative, announced in 2016, proposed using ground-based laser arrays to accelerate extremely small, lightweight probes to approximately 20% of the speed of light. At that velocity, such a probe could theoretically reach Proxima Centauri, the nearest star to our Sun, in roughly 20 years. It is an ambitious concept, and even if the considerable engineering challenges are eventually solved, the technology is designed for interstellar distances measured in single-digit light-years, not intergalactic distances measured in millions. But let us be as generous as the physics allows. Let us grant a civilization more advanced than ours the ability to build a crewed spacecraft capable of sustained travel at 10% of the speed of light. Not the 20% of Starshot's laser-driven probes, but a more conservatively assumed 10% for a vehicle large enough to carry human beings and the systems necessary to keep them alive. 10% of the speed of light is approximately 67 million miles per hour, nearly 2,000 times faster than Voyager 1. Achieving this velocity with a crewed vehicle of any meaningful mass would require energy outputs and propulsion efficiencies so far beyond current capability that no serious engineering roadmap exists for producing them on any near-term horizon. But grant the assumption, at 10% of light speed, the journey to Andromeda would take 25 million years. 25 million years. To place that duration in biological context, 25 million years ago, the ancestors of modern great apes had not yet diverged from the ancestors of old world monkeys. The Himalayas were still being actively pushed upward by the ongoing collision of the Indian and Eurasian tectonic plates' younger mountains than the travel time. The entire evolutionary lineage that produced modern humans, every ancestor from early Miocene primates, through Australopithecines, through Homo habilis, through Homo erectus, through archaic Homo sapiens, to anatomically modern people, fits inside this travel time with tens of millions of years to spare. A spacecraft that departed the Milky Way at 10% of light speed, at the moment the first primitive primates were exploring early Oligocene forests, would be arriving at Andromeda roughly around now. The passengers who boarded that ship, if biological passengers were even a coherent concept for such a journey, would need to sustain not merely themselves, but an entire functioning society, a closed and self-repairing ecosystem, a stable technological infrastructure, and a coherent collective mission purpose, across a span of time longer than most mammalian species, persist on Earth from first appearance to extinction. The average lifespan of a mammalian species in the fossil record is roughly 1 to 2 million years. The journey to Andromeda, at 10% of light speed, would outlast entire evolutionary lineages by a factor of more than 10. Increase the speed. Assume 50% of light speed, a velocity so extreme that achieving it would require harnessing energy sources far exceeding the total current energy output of human civilization. At 50% of light speed, approximately 335 million miles per hour, the journey to Andromeda takes 5 million years. 5 million years ago, the first members of the genus Ardipithecus were appearing in Africa, small-brained, bipedal hominins, separated from us by the entire span of human evolution. Everything that separates those early hominins from you, every tool, every word, every idea, every city, every war, every scientific discovery, every piece of art, every moment of love, or grief, or wonder in the human record occurred within the travel time of a 50% light speed spacecraft trying to reach the next galaxy. Push the speed to 99% of light speed. Here, Einstein's special theory of relativity enters the picture in a consequential way. At velocities approaching the speed of light, time passes more slowly for the traveler relative to a stationary observer, a phenomenon called time dilation, experimentally confirmed with atomic clocks flown on fast-moving aircraft and satellites. The effect is real, measured, unambiguous. For a traveler aboard a spacecraft at 99% of light speed, subjective time would be compressed. The universe outside the ship would age faster than the occupants within it. But here is the number that deflates even this apparent escape route. At 99% of light speed, the external journey time, the time that elapses for observers back in the Milky Way, would still be approximately 2.5 million years. The universe does not care how fast you travel. 2.5 million light-years of distance requires a minimum of 2.5 million years for anything traveling at or near light speed to cross, as measured by stationary observers. Time dilation compresses the traveler's subjective experience. It does not compress the universe's geography. A spacecraft traveling at 99% of light speed experiences roughly a factor of 7 compression in subjective time relative to the external universe. This means that the onboard elapsed time for a crossing that takes 2.5 million external years would be reduced to roughly 357,000 years. Better, dramatically better, than any subrelativistic speed. But 357,000 years is still longer than the entire history of anatomically modern Homo sapiens on Earth. The passengers, or their biological descendants, even assuming perfect life extension technology, would arrive after a subjective journey spanning the entire evolutionary timeframe of our species. What about 1g constant acceleration, the scenario sometimes cited as the most physically elegant approach to near light speed travel? A spacecraft that could sustain a constant acceleration of approximately 9.8 meters per second squared Earth normal gravity for the passengers, conveniently providing artificial gravity throughout, would naturally reach near light speed and benefit from relativistic time dilation to its maximum extent. Under this scenario, the subjective journey time to Andromeda could be reduced to roughly 28 years of experience time. 28 years. A crew could board in young adulthood and arrive in late middle age. The premise sounds, finally, almost like something discussable in human terms. But this scenario conceals problems so severe and so fundamental that they effectively remove it from any serious consideration as a practical possibility. The first problem is energy. Maintaining 1g constant acceleration for a 2.5 million light-year journey. For a spacecraft of any meaningful mass, he would require an energy expenditure so enormous that no known or theorized fuel source comes remotely close to providing it. The energy required to accelerate a spacecraft of reasonable mass to 99-point-something% of light speed, sustain that acceleration, and then decelerate at the destination exceeds the total energy output of our Sun over significant fractions of its entire lifetime. We are not talking about a difficult engineering problem awaiting a clever solution. We are talking about energy requirements that would consume stellar-scale power sources Entire stars burned as fuel for a single voyage. The second problem is more profound, and no amount of engineering can address it. The travelers who arrived at Andromeda after 28 subjective years would step out of their spacecraft into a universe that had aged by 2.5 million years during their journey. Every person they knew would be gone, not dead for a few generations, but gone for 2.5 million years. Every civilization they left behind would have risen, collapsed, transformed, or vanished across millions of years of history they were not present for. Every record of their departure would be archaeological artifact at best. The stars of the Milky Way they left behind would have shifted in their orbits within the galaxy. The Milky Way itself would look different. Their home star might have entered its red giant phase. Earth, if it still existed, would be unrecognizable. They would arrive not just as strangers, but as time travelers from a past so remote that the separation between their departure moment and the universe they arrived into would dwarf the entire human evolutionary record by a factor of nearly 10. They would not be travelers who had gone far. They would be travelers who had effectively gone to a different era of cosmic history, one with no connection to anything that existed when they left. And the galaxy they were aiming for would not be the Andromeda they studied before departure. The maps they carried would describe a galaxy that had aged 2.5 million years since those maps were made. Massive blue stars that blaze prominently in their navigational charts would have exhausted their fuel and exploded as supernovae, leaving behind neutron stars or black holes where bright landmarks once burned. Millions of new stars would have formed in regions that were cold gas clouds when the mission was planned. The spiral arms would have rotated into different configurations around Andromeda's center. Individual star systems, used as navigational targets, would have shifted their positions within the galaxy by measurable distances. They would arrive carrying charts of a galaxy that no longer existed in that form, navigating by stellar landmarks that had changed or vanished entirely across the 2.5 million year travel time. The destination would not be the place they left to find. It would be its own distant descendant, the Generation Ship, a category error. Generation Ship spacecraft designed to carry self-sustaining human populations across journeys, too long for any individual to survive, with descendants eventually arriving at the destination, while original passengers accept they will never see it, represent the most commonly proposed workaround for the biological limitations of interstellar and potentially intergalactic travel. The concept has genuine romantic appeal. It reframes a journey from an individual endurance test to a collective civilizational project, spanning evolutionary timescales and representing the kind of long-term commitment to a purpose larger than any individual life that human beings sometimes achieve in their grandest endeavors. Cathedrals built across generations, scientific projects spanning centuries, the slow multi-generational accumulation of knowledge across millennia. But applying the generation ship concept to intergalactic distances does not stretch the concept to its limit. It reveals a qualitative boundary between problems that are merely very hard and problems that are categorically different in kind. At 10% of light speed, the optimistic velocity we granted earlier, a generation ship bound for Andromeda would need to sustain a functioning human population for 25 million years. Consider what that actually requires, with full honesty about what engineering means across those timescales. It requires a closed ecosystem capable of recycling every molecule of water, every unit of atmospheric gas, every calorie of food, without any external resupply, without any supplementation, without any correction from outside, for 25 million years. Every natural ecosystem on Earth, every forest, every ocean, every grassland, depends on inputs from outside itself: solar energy, atmospheric exchange with the planetary system, geological inputs from volcanism and erosion, biological exchange with adjacent ecosystems. A closed-loop life support system, severed from all external inputs, must do what no natural or artificial ecosystem has ever done, for a duration roughly 800 times longer than all of recorded human civilization. It requires a social structure stable enough to maintain collective purpose and institutional memory across approximately 1 million human generations, assuming a generation every 25 years. Consider that most human institutions, in the historical record, do not survive 100 generations. The longest continuous institutions in human history, certain religious organizations, a handful of universities, a small number of states have persisted for perhaps 200 or 300 generations, and even these have transformed so thoroughly across that time as to bear only nominal continuity with their founding forms. A generation ship to Andromeda would need institutions 100,000 times more durable than the most persistent institutions humanity has ever built. It requires materials that resist degradation across 25 million years of continuous use in the radiation environment of intergalactic space, farther from any star than any human-made structure has ever operated, exposed to cosmic rays and the tenuous particle background of the intergalactic medium, subjected to the accumulated stress of millions of years of thermal cycling, vibration, and the slow degradation that affects all materials over sufficient time. No material humanity has ever manufactured has been tested across anything approaching this duration. The oldest manufactured objects on Earth's stone tools have survived hundreds of thousands of years through the fortunate accident of geological burial and preservation, not through engineered resistance to active degradation. It requires maintaining genetic diversity within the founding population across 25 million years of reproduction, a population genetics challenge that has no solution in any human-scale framework of analysis. Genetic drift, mutation accumulation, and the biological pressures of a closed population would transform any founding group into something biologically and cognitively unrecognizable within hundreds of thousands of years, let alone millions. The species that arrived at Andromeda would not be Homo sapiens in any meaningful biological sense. If every human being who has ever lived, all 110 billion individuals, estimated across the 300,000-year history of anatomically modern Homo sapiens on Earth, participated in a relay race in which each person ran one leg and passed a baton to the next, that relay would cover approximately 300,000 years from start to finish. The generation ship journey to Andromeda, at 10% of light speed, would require that relay to be repeated 83 times consecutively, without interruption, without any external contact, without the possibility of resupply or rescue before the destination was reached. The generation ship concept applied to intergalactic distances is not a difficult engineering problem. It is not a challenge awaiting sufficiently advanced technology. It is a category error, an attempt to apply a framework designed for a qualitatively different scale of problem to one that exceeds it by so many orders of magnitude that the original framework has lost its meaning entirely. The difference between an interstellar generation ship journey measured in decades or centuries and an intergalactic generation ship journey measured in millions of years is not a difference in degree. It is a difference in kind, as fundamental as the difference between swimming across a river and swimming across an ocean, or more precisely, as the difference between swimming across a river and swimming to the moon. The physical boundary. This leads to the hardest realization in this entire story. The distance to Andromeda is not merely a very large number. It is a physical boundary, not a wall in the literal sense, not a barrier made of matter or energy blocking the path. Something more fundamental, a boundary imposed by the geometry of space, the speed of light, the energy requirements of acceleration, and the biological limitations of every known form of life. Within the framework of known physics, the intergalactic void between the Milky Way and Andromeda constitutes a permanent separation for any biological civilization confined to sub-light-speed travel. Permanent. Not temporarily beyond reach. Not awaiting a future technological breakthrough. Not a problem that clever engineering will eventually dissolve. Permanently inaccessible within any time frame that a biological species, a culture, a continuous line of technological development, any coherent form of life with finite duration, could realistically sustain. This is not a statement about human ambition or human intelligence. It is a statement about the architecture of the universe. The cosmos built its structures on scales that do not accommodate biological travel between galaxies. The same laws of physics that allow stars to form, planets to coalesce from circumstellar disks of dust and gas, and chemistry to become biology also impose speed limits, energy constraints, and distance scales that confine any civilization born within a galaxy to that galaxy. The Milky Way is not a launching pad for intergalactic exploration. It is, for all practical purposes within known physics, the entire accessible universe for any species that calls it home. Even within the Milky Way, the distances are staggering. The nearest star to our Sun is 4.25 light years away, a distance that Voyager 1 would need 73,000 years to cover. The galaxy spans 100,000 light years. A civilization that somehow mastered interstellar travel at 10% of light speed could explore a significant fraction of the Milky Way over millions of years, seeding itself across thousands of star systems, building a network of inhabited worlds of extraordinary scope. The Milky Way alone contains enough territory, enough stars, enough planets, enough variation in stellar types and planetary environments that it could occupy a civilization's attention and ambition for the entire remaining lifespan of the galaxy. No civilization that has ever existed on Earth has exhausted the exploratory possibilities of the continent it first appeared on, let alone the planet it inhabits, let alone the solar system surrounding it. The jump from within our galaxy to between galaxies is not a step up in scale. It is a chasm so wide that it effectively marks a boundary in what is physically achievable. The distance to Andromeda is 25 times the diameter of the entire Milky Way. It requires crossing 2.5 million light years of empty space, with no stars to visit along the way, no resources to harvest, no gravitational assists to exploit, no intermediate destinations for any conceivable form of resupply or course correction. It is the longest, emptiest crossing conceivable, and it must be completed in a single, unbroken journey spanning millions of years. Here is an analogy that captures the proportional relationship honestly. Imagine an ant standing on a globe placed on a table in the middle of a vast, completely featureless desert. Somewhere in that desert, separated from the first globe by several miles of flat, empty sand, sits a second globe identical in size, equally isolated. The ant can comprehend direction. It can orient itself. It could, in principle, begin walking toward where the second globe must be, based on whatever information it was given about the direction and approximate distance. But the distance between the two globes would exceed every capability the ant possesses by so many orders of magnitude that the journey would be meaningless before it was well begun. The ant would die before covering a fraction of a percent of the distance. Its descendants, if they somehow continued the journey with perfect fidelity of purpose, would face the same limitation for each subsequent generation. The desert is simply too wide for the organism attempting to cross it. Not because the ant is deficient, not because the desert is hostile, but because the scale of one is fundamentally incompatible with the capabilities of the other. That is the relationship between human civilization and the distance to Andromeda. Not a relationship of inadequacy waiting to be addressed by better technology. A relationship of fundamental incompatibility between the scale of the universe's structures and the capabilities of the biology that evolved within one of those structures. The cosmos built galaxies. The cosmos built the distances between them. And then, as a kind of secondary and entirely incidental event in the margins of a story being told on a much larger scale, the cosmos allowed chemistry to become life within one of those galaxies. That life, by the improbable accident of intelligence, eventually became capable of measuring the distances between the structures it inhabits. But measuring a distance and crossing it are different things. And the architecture of the universe, it turns out, was not designed with the latter in mind. What your eyes can do, that your body cannot. Stand outside on a clear autumn night. Find the constellation Andromeda, the line of stars, extending from the northeast corner of the Great Square of Pegasus. Look along that line and find the faint smudge that ancient astronomers cataloged as a local cloud of gas, that for centuries was assumed to be a minor feature of our own galaxy's interior, and that on a single night in the early 1920s was revealed to be something else entirely. Hold your gaze there for a moment. What you are looking at is the combined glow of 1 trillion stars burning across a disk of space 220,000 light-years wide, located 2.5 million light-years from your eyes. The photons entering your retina at this moment left that galaxy before your species existed, before any member of your genus had yet evolved, before the first stone tool had been deliberately struck, before language, before fire, before the entire arc of human history had begun its unlikely unfolding on a small rocky world in the outer suburbs of the smaller of the two gravitationally bound spirals, making up this local corner of the cosmos. That light has been traveling for 2.5 million years to reach you. It crossed the intergalactic void, 14.7 quadrillion miles of near-perfect vacuum, the emptiest natural environment in the known universe, and it ended its journey on the surface of your eye, converted into an electrical signal by photoreceptor cells in your retina, transmitted through your optic nerve. Processed by a brain that weighs approximately 3 pounds, consumes roughly 20 watts of metabolic power, and fits inside a skull you can hold in your 2 hands. You cannot go there. No technology you will plausibly ever build in your lifetime, in your civilization's current trajectory, in any time frame bounded by the remaining lifespan of our sun, can take any biological organism from the Milky Way to the Andromeda galaxy. The distance is too vast. The time required is too long. The energy requirements are too extreme. The biology is too fragile and too brief. Andromeda will remain, permanently, and by the unalterable verdict of physics, beyond the physical reach of any human being, any human civilization, and quite possibly any biological organism that will ever evolve within the Milky Way. But you can see it, right now, tonight, with your own unaided eyes. And this is where the story makes its most unexpected turn, because seeing is not a consolation prize for an organism that cannot travel. Seeing, in this context, is something more radical than that, something that deserves to be examined carefully and without the false comfort of easy sentiment. You can see Andromeda. You can also measure it, using the same physical principles that Hubble used on that cold California night, the predictable pulsations of Cepheid variable stars, and using the far more powerful instruments built by the generations that followed him. Astronomers have measured the distance to Andromeda with extraordinary precision. They have calculated its total mass, its dark matter halo, its rate of approach. They have counted its globular clusters, measured the mass of its central black hole, mapped its spiral arms with infrared telescopes capable of seeing through the dust that blocks visible light, identified individual star-forming regions within it, detected the signatures of its satellite galaxies being tidally disrupted by its gravity, and modeled with all the honest uncertainty we discussed earlier the future gravitational encounter between Andromeda and our own galaxy. All of this has been done from the surface of a single planet, orbiting a single unremarkable star in the quiet middle suburbs of the smaller of the 2 galaxies in question. The instruments used were built by a species that had not yet invented writing when the light they captured first began its journey. The mathematics used to interpret the measurements was developed within the last few centuries by minds that had no idea what they would eventually be used to describe. The entire scientific infrastructure, the telescopes, the computers, the international collaborations, the accumulated theoretical framework represents the work of tens of thousands of people across generations, none of whom expected to be contributing to the measurement of intergalactic distances when they first sat down to do mathematics or look through a lens. And yet, collectively, from this small outpost of biology on a small rock in space, they measured a structure containing 1 trillion stars sitting 2.5 million light years away. They determined that it is approaching. They predicted what will happen when it arrives. They calculated that the sun is unlikely to collide with any other star during the entire process, despite the merger of 2 systems each containing hundreds of billions of stars. They are still refining the details, the precise transverse velocity, the exact timeline, the specific geometry of the first close approach, and may continue refining them for decades. This is not a small thing. This is, arguably, the most extraordinary capability that biology has ever developed on this planet, or, as far as we know, anywhere in the observable universe. The paradox, at the center of everything. There is a paradox sitting quietly at the heart of this entire story, and it has been there since the beginning, waiting for the moment when all the measurements were laid out clearly enough for it to become visible. The paradox is this: the same species that is too small, too fragile, too brief, and too slow to reach the nearest giant galaxy, is the only known species in the universe that has measured it. This is not a comfortable paradox. It does not resolve neatly into either triumph or despair. It refuses to be used simply as a source of inspiration, and it refuses to be used simply as a source of humiliation. It is a genuine tension between 2 real facts, the fact of confinement and the fact of comprehension that exists simultaneously, without canceling each other out, and that together define the strangest position any known form of matter has ever occupied in the history of the cosmos. Let us examine both sides of it carefully, and without flinching from either one. On one side, the confinement is total. We have done the arithmetic. We have traced every trajectory, examined every proposed propulsion system, followed every speculative technology to its logical conclusion within the bounds of known physics, and arrived at the same answer each time. The intergalactic distance is not a challenge awaiting a solution. It is a structural feature of the universe that no form of biology operating under known physical laws can overcome within any time frame that connects meaningfully to the life that attempts the crossing. 2.5 million light-years of near-perfect vacuum crossed at the maximum speed the universe permits requires 2.5 million years. No shortcut has been observed. No loophole in the physics has been confirmed. The distance is the distance. The speed limit is the speed limit. And the biology is the biology. And the biology is, by any objective measure, astonishingly brief and astonishingly fragile. Human beings live for roughly 80 years under favorable conditions. Our species, in its current anatomically modern form, has existed for approximately 300,000 years. An eye blink in geological time, a subatomic flicker in cosmic time. The civilization capable of building telescopes and calculating intergalactic distances has existed for only a few centuries. The oldest continuously operating scientific institution on Earth is younger than the time it takes light to cross a moderately large stellar nebula. We are, in the universe's terms, a phenomenon so recent and so brief that the word new does not begin to capture the disproportion. Our bodies are built for a planet. Gravity calibrated exactly to Earth's surface. Atmospheric pressure suited to a column of air roughly 60 miles thick. Temperature ranges that constitute a narrow band between the freezing and boiling points of water. Radiation shielding provided by a magnetic field and an ozone layer that we did not build and cannot replicate on any meaningful scale beyond a single habitat module. Remove any one of these conditions, and the body fails within minutes to days. The universe beyond Earth's surface is, with the exception of a few carefully engineered environments, humans have temporarily occupied, uniformly lethal to us. The vacuum of space kills. The radiation of interplanetary space accumulates to dangerous doses over months. The microgravity of extended spaceflight degrades bone density, muscle mass, cardiovascular function, and immune response in ways we are still working to understand and mitigate. We have not sent a human being beyond low Earth orbit since 1972. We have never sent a human being beyond the Moon. The nearest planet that might conceivably support some form of extended human presence, Mars, is a world with no breathable atmosphere, no liquid water on its surface, negligible magnetic field protection from solar and cosmic radiation, and surface temperatures that average around -80 degrees Fahrenheit. And Mars is, by cosmic standards, our next-door neighbor. This is the full weight of the confinement. Not just the intergalactic distances, but the entire cascade of physical constraints that applies to biology in space. We are creatures of a very specific, very narrow, very particular set of conditions. And the universe is almost entirely made of conditions that are not those. On the other side, we measured Andromeda from here. From this planet, under these conditions, within these biological constraints, using instruments built over a few centuries, by a species that had spent most of its existence as a nomadic animal with no mathematics, no writing, and no concept of a galaxy. This second fact does not cancel the first. The confinement is real, but the comprehension is also real. And the combination of the two, the simultaneous reality of absolute physical limitation and extraordinary cognitive reach, is what makes the human position in the universe genuinely strange, in a way that few other facts about existence can match. The brain that measures the universe, it cannot reach. Consider what the act of measuring Andromeda actually involves, at the level of the physical object doing the measuring. The human brain weighs approximately 3 pounds. It occupies a volume of roughly 1.5 liters, about the size of a small cantaloupe. It runs on approximately 20 watts of metabolic power, derived from glucose and oxygen delivered by the cardiovascular system. It is made of approximately 86 billion neurons, each one a biological cell that evolved from much simpler predecessors over hundreds of millions of years of incremental modification. The entire structure developed from a single fertilized cell through an embryological process that takes 9 months and requires no conscious direction from the organism it is building. This object, this 3-pound lump of electrochemical tissue running on the caloric equivalent of a dim, incandescent light bulb, developed within the last few centuries. The capacity to determine that a faint smudge of light in the autumn sky is a galaxy containing 1 trillion stars, located 2.5 million light-years away, moving toward our galaxy at 250,000 miles per hour, with a central black hole massing 100 million solar masses. It did this not by traveling there, not by sending anything there, not by direct observation at close range. It did this by developing a sequence of abstract mathematical and physical principles: the inverse square law governing light intensity, the period luminosity relationship of Cepheid variable stars, the Doppler effect governing the shift in spectral lines from moving objects, the theory of general relativity governing the behavior of gravity at galactic scales, the statistical mechanics of stellar populations, and applying them to the analysis of light that had spent 2.5 million years traveling to reach the instruments attached to the brains doing the analysis. The entire measurement is an exercise in inference. Nothing about Andromeda was touched, sampled, or directly examined. Every fact we know about it was extracted from the pattern of electromagnetic radiation that left it millions of years ago and arrived at telescopes on Earth, where it was recorded, analyzed, and interpreted through layers of mathematical and theoretical framework developed by thousands of scientists across generations. The galaxy's distance was inferred from the pulsations of a variable star, using a relationship discovered by a woman examining photographic plates at a desk in Massachusetts. Its velocity was inferred from the compression of spectral lines, using a physical principle described by an Austrian physicist in the 19th century. Its mass was inferred from the orbital velocities of its satellite galaxies, using gravitational theory developed by a man in England, working with observations of planets in our own solar system 350 years ago. Every tool used to measure Andromeda was developed for other purposes, in other contexts, with no intention of being applied to the problem of intergalactic measurement. The gravitational theory was developed to describe the motion of planets around the Sun. The spectroscopy was developed to analyze the chemical composition of terrestrial materials in laboratory settings. The period luminosity relationship was discovered by a researcher who was systematically cataloging the properties of a specific category of variable star without any particular application to distance measurement in mind. Each piece of knowledge was built on the foundation of previous knowledge, assembled over generations, with no master plan and no predetermined destination. And the result of all this accidental, undirected, multi-generational accumulation of abstract knowledge developed on a planet that from the perspective of the galaxy it inhabits is invisible, is that we know more about Andromeda than we know about the bottom of our own oceans. We know Andromeda's distance to within a margin of error of a few percent. We know the mass of its central black hole to within an order of magnitude. We know its approach velocity to within a few kilometers per second. We know the distribution of its stellar populations, the ages and chemical compositions of different regions within it, the structure of its spiral arms, the orbits of its satellite galaxies, the signatures of past merger events preserved in the streams of tidally stripped stars that trail through its outer halo. We have mapped its dark matter halo by its gravitational effects on visible matter. We have modeled the future gravitational interaction between Andromeda and our galaxy, and produced predictions about the likely outcomes of that interaction that we can test, refine, and improve as measurement techniques advance. All of this from a pale blue dot, using instruments that fit within a building, operated by beings that fit within a medium-sized car, running on brains that fit within a cereal bowl. The universe is approximately 93 billion light-years across in its observable extent. It contains an estimated 2 trillion galaxies, each one a structure comparable in scale to the Milky Way or Andromeda. The total number of stars in the observable universe is estimated at somewhere around 2 × 10 to the 23rd power, a number so large that writing it out in decimal notation would require a line of digits longer than most roads. The total number of planets is comparable, and within some fraction of those planets, around some fraction of those stars, within some fraction of those 2 trillion galaxies, conditions may exist that permit chemistry to become biology. And within all of that, within the entirety of 2 trillion galaxies and their incomprehensible combined stellar populations, there is exactly one place we know of where biology became capable of measuring the rest of it. Here, on this planet, in these brains, the radiosphere and the silence beyond it. There is one more measurement that deserves its place in this story, because it captures the full scale of our cosmic position in a single, quietly devastating image. Every radio transmission humanity has ever produced, every broadcast signal, every radar pulse, every military communication, every television transmission, every digital data packet sent through wireless systems, every intentional and unintentional electromagnetic emission our civilization has generated since Guglielmo Marconi demonstrated radio communication in the 1890s has been radiating outward from Earth at the speed of light, continuously since the moment of its generation. These signals do not stop. They do not degrade to zero. They thin with distance, following the inverse square law, becoming progressively fainter as the wavefront expands outward in a sphere centered on Earth. But they continue spreading. This means that there is a sphere of electromagnetic noise, centered on Earth, expanding outward through the galaxy at the speed of light, that marks the boundary of humanity's involuntary announcement of its own existence to the cosmos. The radius of this sphere, measured from its origin in the late 19th century to the present day, is approximately 130 light-years. 130 light-years in every direction from Earth. That is the full extent of the region of the galaxy that has had any opportunity to detect that something technological is happening here. 130 light-years sounds, at first, like a respectable distance. And by human standards, it is. Light needs 130 years to cross it. No human spacecraft has come anywhere close to approaching it. It represents a sphere of space, containing thousands of star systems. But the Milky Way is 100,000 light-years across. Our radiosphere, humanity's entire electromagnetic footprint projected into the galaxy over more than a century of technological civilization, covers approximately 0.13% of our own galaxy's diameter. If the Milky Way were the surface of the Earth, our radiosphere would be a circle roughly 15 miles across, a medium-sized county. In a planet, to any civilization observing from the far side of the Milky Way, from 50,000 or 80,000 light-years away, humanity does not exist. Our signals have not arrived. They will not arrive for tens of thousands of years. And when they do arrive, if there is anything watching, they will have been traveling for so long, thinned by the inverse square law for such an enormous distance, that detecting them would require sensitivity in receiving instruments that we ourselves cannot yet build. We have been broadcasting our presence for over a century, and the vast majority of our own galaxy has not yet had the opportunity to hear it. If the Milky Way contained a civilization on every star, an absurd overestimate, but useful as an illustration, and each of those civilizations was listening for electromagnetic signals from others, the overwhelming majority of them would currently have no evidence of our existence. Not because they are not looking, because the signals have not arrived. We are, in electromagnetic terms, almost entirely invisible. Not deliberately, not through any failure of effort, simply because we are small. Our transmitters are weak relative to the distances involved, and we have not been broadcasting for very long. The universe is old, we are new. The light cone of our existence, the region of space-time that we have had any opportunity to influence or be influenced by, is a tiny bubble in an ancient cosmos. And yet, within that bubble, we measured Andromeda. We measured it before our signals had even reached the nearest few thousand stars in our own galaxy. We built the instruments, developed the mathematics, and extracted the distance, velocity, and physical properties of a galaxy 2.5 million light-years away from inside a radiosphere, 130 light-years across, on a planet whose electromagnetic footprint has not yet reached the majority of its own stellar neighborhood. This is the full scale of the disproportion between what we are and what we know. We are electromagnetically invisible to most of our own galaxy. We are physically confined to a single star system. We are biologically unsuited to the conditions that make up approximately 100% of the observable universe. We have existed as a technological civilization for less time than it takes light to cross a modest stellar nebula. And we have determined the mass, distance, velocity, stellar population, black hole mass, spiral arm structure, dark matter distribution, satellite galaxy inventory, and future collision timeline of the nearest giant galaxy. The terrifying truth, stated plainly. We have traveled far enough in this story to state the terrifying truth directly. Not as a dramatic conclusion, but as a plain, measured description of what the evidence actually shows. The terrifying truth about our size in the universe is not simply that we are small. Smallness alone would be manageable as a fact. Many things are small. Electrons are small. Atoms are small. The Earth is small relative to the Sun, and the Sun is small relative to the galaxy, and the galaxy is small relative to the observable universe. Scale is relative. Smallness in isolation is not inherently frightening. It is not even particularly interesting without context. The terrifying truth is more specific than that. It is the combination of three facts that exist simultaneously and cannot be separated from each other without losing the full force of what they mean together. The first fact: we are small enough to be permanently confined, not temporarily confined, awaiting a technological solution. Not confined in principle, but free in theory. Permanently confined by the architecture of the universe itself, by the speed of light, by the energy requirements of acceleration, by the distances between galactic structures that were set in place by the physics of galaxy formation billions of years before biology evolved to one galaxy among an estimated 2 trillion. We are prisoners of the Milky Way, not through any failure of our own, but through the fundamental incompatibility between the scale of intergalactic space and the capabilities of any biology operating under known physical laws. The second fact: we are capable enough to measure what confines us. Not approximately, not vaguely. With extraordinary, quantitative, reproducible precision. We can measure the distance to Andromeda. We can calculate its mass. We can determine its velocity. We can model its future gravitational interaction with our galaxy. We can identify the signatures of individual supernova remnants within it, map the distribution of its stellar populations by age and chemical composition, and track the tidal disruption of its satellite galaxies in real time. We can do all of this from the surface of the planet we are confined to, using instruments that fit within buildings, operated by beings that fit within rooms. The third fact: the measurement does not diminish the confinement, and the confinement does not diminish the measurement. These two realities coexist without resolving into each other. Seeing Andromeda does not mean we can reach it. Being unable to reach it does not mean we cannot understand it. The universe allowed biology to develop in one of its structures, and that biology, by an accident of evolutionary pressure toward complex problem solving, developed the capacity to comprehend the structure of the universe around it without being able to move through most of it. There is no reason this should be the case. There is no evolutionary pressure that specifically required animals on a small planet to develop the capacity for intergalactic distance measurement. It happened as a byproduct of a general capacity for abstract reasoning that conferred survival advantages on much smaller scales, tracking prey across a landscape, anticipating the behavior of rivals, planning across seasons. The application of that general capacity to the measurement of cosmic distances was an accident of culture, of accumulated knowledge, of the particular directions human curiosity happened to take across the last few thousand years. The universe did not design us to understand it. It does not require us to understand it. It was doing everything it does, forming galaxies, evolving stars, generating and destroying planetary systems, maintaining the approach of Andromeda toward the Milky Way for billions of years before we arrived, and it will continue doing all of it for billions of years after we are gone. Our understanding of it changes nothing about what it does. The measurement of Andromeda does not affect Andromeda's trajectory by a single kilometer per second. And yet the measurement happened. From here, now, with these instruments, using these brains, what it means to stand here. You are reading or listening to these words on a planet 7,900 miles across, orbiting a star 864,000 miles in diameter at a distance of 93 million miles in a solar system whose outermost planetary orbit spans nearly 3 billion miles. within a galaxy 100,000 light-years across, containing up to 400 billion stars, which is itself the smaller of two gravitationally bound spirals, separated by 2.5 million light-years of near-perfect vacuum, moving toward each other at 250,000 miles per hour in a gravitational interaction that will unfold across the next several billion years. Every number in that sentence is real. Every distance has been measured. Every velocity has been confirmed. Every structure described has been observed, analyzed, and documented by instruments built by the species that is the subject of the description. You exist at a specific address in the cosmos, not a metaphorical address, a literal, measurable, physical location in the hierarchy of structures that make up the observable universe. You are on a rocky planet around a G-type main sequence star in the Orion spur of the Sagittarius Carina minor arm of a barred spiral galaxy called the Milky Way, which is gravitationally bound to a slightly larger spiral galaxy called Andromeda, within a loose collection of more than 80 galaxies called the Local Group, within a larger clustering of galaxy groups called the Virgo supercluster, itself a tendril of a vast cosmic web structure called Laniakea, a gravitational supercluster spanning roughly 500 million light-years that contains hundreds of thousands of galaxies and represents the largest structure within which our galaxy's motion is gravitationally influenced by the surrounding distribution of mass. That is your address. That is where you are. And most of it, the overwhelming, crushing, almost incomprehensible majority of it, you will never visit. You will never leave the first item on that list, the rocky planet. You will live your entire life on that single item in the cosmic address, covering, if you are very mobile, a few tens of thousands of miles of its surface. A few million people in human history have left the planet's surface briefly, in vehicles not designed for any extended stay beyond it, and returned. 12 of them walked on the surface of the moon. None of them went further. This is not a failure. This is the condition of biology in the universe that produced biology. It is the condition described by every measurement in this story, stated plainly and without softening. But something else is also true. While your body has spent its entire existence within a few thousand miles of the surface of one planet, your knowledge has not been so confined. The 3-pound brain inside your skull has participated through the accumulated inheritance of human scientific knowledge, through every book and lesson and conversation and observation that built the framework through which reality is understood in the measurement of the cosmos that surrounds and vastly exceeds it. You know things about the universe that the universe did not make it easy to know. You know the distance to Andromeda. You know the mass of its central black hole. You know that the light arriving from it tonight left that galaxy before your species existed. You know that it is approaching, that it will eventually merge with the Milky Way in an event measured in billions of years, and that your sun will most likely survive the merger as a displaced but intact star in the outer regions of the merged galaxy, renamed Milkdromeda, or something we have not settled on yet, orbiting the combined center of mass of two ancient spiral systems in a sky no longer recognizable to any astronomical tradition that has ever existed on Earth. You know all of this not because you traveled there, but because the species you belong to developed, through accidental, cumulative progress over centuries, the capacity to extract information from light that traveled from Andromeda to here over millions of years. You are the beneficiary of an unbroken chain of intellectual labor, stretching back through every astronomer, physicist, mathematician, and instrument builder, whose work contributed to the framework through which the night sky is now understood. The ancient observers who cataloged the stars, the medieval Islamic astronomers who preserved and extended Greek astronomical knowledge, Copernicus, who displaced Earth from the center of the solar system, Galileo, who first pointed a telescope at the sky and saw Jupiter's moons and Saturn's rings and the phases of Venus, Newton, who showed that the same gravity binding an apple to a tree governs the orbits of planets around the sun, Henrietta Swan Leavitt, who measured the pulsations of Cepheid stars and gave astronomy its first reliable cosmic yardstick, Edwin Hubble, who used that yardstick to measure Andromeda's distance and double the known universe in a single night. Every one of them contributed a piece of the framework that allows you, standing in a backyard on a clear autumn night, to look at a faint smudge of light and know with genuine, quantitative, reproducible certainty that you are seeing 1 trillion stars, 2.5 million light-years away. The scale of what was built. To understand the scale, there is something worth pausing on in the specific character of the knowledge that allows us to measure the cosmos. The knowledge is not intuitive. Nothing about the size of the universe, or the distances between its structures, or the timescales on which it operates, is accessible to unaided human intuition. The brain that evolved on the African savanna has no natural faculty for comprehending light years, for feeling the weight of 1 trillion solar masses, for intuitively grasping the difference between 1 million and 1 billion years. These things are outside the range of any experience that natural selection ever had reason to equip us for. The universe does not require animals to understand it in order to survive within the thin biosphere of a terrestrial planet. The knowledge is entirely constructed. It was built, piece by piece, through deliberate effort, over centuries, using tools that had to be invented before they could be used, applying methods that had to be developed before they could be applied, within a framework of mathematics that had to be progressively elaborated before it could be brought to bear on cosmic scale problems. None of it was given. All of it was made. And the process of making it was not smooth or linear. It involved wrong turns, false starts, bitter disputes, delayed recognitions, and repeated failures. The heliocentric model of the solar system was proposed, suppressed, revised, and eventually accepted over more than a century of struggle. The true scale of the Milky Way was debated for decades, with estimates ranging by orders of magnitude depending on what assumptions were made about the distribution of dust absorbing light within the disk. The question of whether the spiral nebulae were objects within our galaxy or separate galaxies entirely, the great debate was unresolved for years before Hubble's Cepheid measurement settled it. The history of cosmic understanding is not a story of steady progress toward truth. It is a story of episodic, hard-won revisions of understanding, each one revealing a universe larger and stranger and more indifferent to human categories than the previous understanding had allowed. Each revision required abandoning a framework that felt complete and correct, and replacing it with one that initially felt disorienting and counterintuitive. The Earth-centered cosmos gave way to the Sun-centered solar system. The Sun-centered solar system revealed a galaxy in which the Sun was one unremarkable star among hundreds of billions. The Milky Way revealed itself as one galaxy among at least 2 in the local pair, which were themselves members of a local group, which was itself a small feature of a supercluster, which was a tendril in a cosmic web that extended across the entire observable universe. At every stage, the answer was bigger, emptier, older, and more indifferent than the previous answer had been. At every stage, the position of humanity in the revised picture was smaller and more peripheral than it had appeared in the version before. The history of astronomy is, in one of its dimensions, a sustained multi-century exercise in the systematic demotion of human centrality. We have been removed from the center of the solar system, removed from any special position within the galaxy, removed from any special position within the local group of galaxies, and given no reason to believe that the portion of the cosmos we occupy is in any way distinguished from any other equivalent portion. And yet, and this is the thing that deserves to be stated clearly, and without the false modesty that sometimes accompanies discussions of human smallness, the species that received this systematic demotion was also the species that administered it. We measured ourselves out of our own perceived centrality. We built the instruments, developed the mathematics, executed the observations, and accepted the results that progressively revealed how small, how peripheral, how brief, and how physically confined we are. We did not resist this knowledge. We pursued it. The human scientific tradition, at its most consistent, has been a sustained effort to see clearly, even when what is seen is uncomfortable, even when the clear view reveals a universe that was not built for us and does not require us. This is not a trivial character. Most cognitive systems, natural or artificial, tend to produce models that place the observer at the center. Intuition consistently overestimates the significance of the immediate and local. The brain that evolved to navigate social hierarchies and track the movement of food sources within a familiar landscape has every natural reason to treat the local as primary and the distant as peripheral or negligible. Overcoming that tendency, building the instruments and methods to extend perception beyond its natural limits, and then accepting the results even when they challenge every intuitive prior, is an achievement with no obvious parallel anywhere else in the observable universe. We do not know if there are other minds in the cosmos capable of the same thing. The universe is large enough and old enough that the absence of confirmed evidence for other technological civilizations is not the same as evidence of their absence. The question remains genuinely open. But we know of at least one place where biology produced a form of cognition capable of measuring the universe that contains it. And that place is here. Whatever the final inventory of cosmic intelligence turns out to be, if it is ever known, this planet will be on the list. The confinement is real, and so is the comprehension. It is important to resist two opposite temptations in responding to the story this journey has told. The first temptation is to find, in the fact of measurement, a solution to the problem of confinement, to read the capacity for comprehension as a form of freedom that transcends the physical limitation, to conclude that because we can know Andromeda, the fact that we cannot go there is somehow beside the point. This is a comfortable conclusion, but it is not an honest one. The confinement is real. The isolation is real. The physical barrier between us and every other galaxy in the observable universe is a genuine feature of the cosmos, not a psychological construct to be dissolved by the right way of thinking about it. No amount of intellectual access to Andromeda will carry a single human being or their descendants across the 2.5 million light years separating us from it. The measurement is real and the barrier is real, and both remain true simultaneously. The second temptation is to read the confinement as a diminishment that makes the measurement pointless. To conclude that because we cannot go anywhere significant in the universe, the fact that we can measure things that are far away is a kind of cosmic mockery, a cruel demonstration of capability without consequence. This is equally dishonest, in the opposite direction. The measurement of Andromeda is not a consolation prize. It is not a participation trophy awarded to a species too small and slow to actually matter in cosmic terms. It is a genuine, irreducible achievement of a category that the universe does not appear to have produced abundantly the capacity for a biological system to comprehend structures incomparably larger than itself, across distances incomparably greater than it can physically traverse, using methods that took centuries to develop and that have no precedent in the evolutionary history of any other form of life we know of. The honest position is to hold both facts at the same time, without resolving the tension between them. The scale is terrifying. The distances are permanent. The isolation is real. And the measurement happened from here. And that is also real. And no scale of universe is large enough to make the fact of that measurement small. The night sky, as a physical object, here is something concrete to take away from this entire journey. The next time you find yourself outside on a clear night, away from city lights, in a place dark enough for the Milky Way to be visible as a band of light across the sky, try to hold in your mind simultaneously everything this story has laid out. The band of light you are looking at is the combined glow of hundreds of billions of stars in the disk of a galaxy, 100,000 light years across. Every star in that band is a sun many larger than ours, most smaller, some burning for billions of years, others destined to explode within millions. The light reaching your eyes from the far side of that band left those stars tens of thousands of years ago, before any recorded human civilization existed. The nearest of those stars are years away at the speed of light. The farthest are tens of thousands of years away. None of them are reachable by any human being alive today, or likely by any human being who will live during the remaining functional lifespan of this civilization. And then, find Andromeda. Look toward the northeast on an autumn evening. Trace the line of stars from the Great Square of Pegasus, and find the faint smudge that does not quite look like a star. Hold your gaze there long enough for your eye to adjust. It is not dramatic. It does not announce itself. It looks, to the unaided eye, like almost nothing. But what you are looking at is a structure containing 1 trillion stars, spread across 220,000 light-years of space, located 2.5 million light-years from your retina. The light you are seeing left that galaxy before the genus Homo existed on Earth. It crossed 14.7 quadrillion miles of near-perfect vacuum, the emptiest natural environment in the known universe, and it is ending its 2.5 million year journey on your eye at this moment. That light will never make any more meaningful contact with this planet. It has been traveling since before your species existed. It arrived tonight. It will be converted by your retina into an electrical signal, transmitted through your optic nerve, processed by your visual cortex, interpreted by your brain as the faint smudge of a distant object in the autumn sky. And within a second or two, the moment will be over, and you will probably look at something else. In that brief interval, the moment between the photons arriving and your attention moving on, something happened that took 2.5 million years to arrange. 1 trillion stars sent light into the void. The void carried it across an incomprehensible distance. The light arrived at a planet where, by an unlikely series of events spanning billions of years of planetary and biological evolution, there happened to be an organism capable of recognizing what it was looking at. You cannot go to Andromeda. The physics will not allow it. The biology will not survive it. The energy requirements are beyond any technology you will see in your lifetime or your civilization's foreseeable trajectory. The distance is permanent, real, measured, and final within the framework of known physical law. But you saw it. You looked at 1 trillion stars, 2.5 million light years away, and you knew what they were. You knew how far they were. You knew they were coming toward you. You knew their combined mass, the size of the black hole at their center, the nature of the gravitational interaction that awaits your galaxy and theirs across billions of years of future cosmic time. You knew all of this. From here, on a rock 7,900 miles across, orbiting an ordinary star in the quiet suburbs of a medium-sized galaxy, using a brain that runs on 20 watts and fits in the palm of your hand, the universe measured from a small place. The Milky Way contains somewhere between 200 billion and 400 billion stars. Current estimates suggest it harbors between 100 billion and 300 billion planets, a meaningful fraction of them orbiting within the habitable zones of their host stars, where conditions might permit liquid water on their surfaces. This single galaxy, the one we are confined to, provides a cosmic territory of such immensity that a civilization traveling at 10% of light speed would need 1 million years to cross it from edge to edge. No species that has ever existed on Earth has maintained a continuous technological civilization for anything approaching 1 million years. The Milky Way alone contains more space, more stars, more planets, more potential destinations, more unanswered questions, and more undiscovered worlds than any civilization could exhaust in the entire remaining lifespan of the Sun. We are not in a prison cell. We are in an arena of almost limitless possibility that we have barely begun to explore. The galaxy we are confined to is, from any reasonable perspective grounded in the actual history of human exploration, effectively infinite. We have visited one star system, ours, and have sent crude robotic emissaries on single flyby trajectories past the planets within it. We have landed robots on 2 planets, and 1 comet, and a few moons. We have placed spacecraft in orbit around 5 bodies in our own solar system, beyond Earth. The inventory of what we have directly accessed physically, as opposed to observed remotely, represents a rounding error in the catalog of what is available within our own galaxy. Andromeda, the giant next door, doubles the accessible territory. Not that we can reach it, but in terms of the sheer scale of what exists nearby in cosmic terms. But it doubles it across a gap that the physics will not let biology cross, which means that all the wonder, and all the challenge, and all the possibility that the cosmos contains for any civilization born in the Milky Way is already here, already available, already within the boundaries of what, in principle, a sufficiently advanced civilization could explore, map, visit, and understand over millions of years of systematic effort. We have not run out of universe. We have barely started on the one we have. 3 pounds of neural tissue in an incomprehensible cosmos. Return, at the end of all this, to where we began. You live on a planet so small that more than 1 million copies of it could fit inside the Sun. That Sun is one of 400 billion stars drifting through a galaxy so enormous that light itself needs 100,000 years to cross it. Next to that galaxy, at a distance of 2.5 million light years, a galaxy called Andromeda stretches across 220,000 light years of space and contains approximately 1 trillion stars. It is larger than the place we call home in every measurable dimension. And right now, it is moving toward us. You are 3 pounds of neural tissue running on the caloric equivalent of a dim light bulb. You live, for approximately 80 years, on a planet 7,900 miles across, orbiting a star that is one among 400 billion, in a galaxy that is the smaller of 2 gravitationally bound spirals, separated by 2.5 million light-years of empty space. You came from biology that cannot survive the vacuum outside your atmosphere. You cannot travel faster than a small fraction of the speed of light. You will die long before any spacecraft launched by your civilization reaches the nearest star to your own sun. And you measured all of it. The size of the Earth, the distance to the sun, the scale of the solar system, the dimensions of the Milky Way, the structure of Andromeda, the distance to Andromeda, the velocity of Andromeda's approach, the mass of its central black hole, the number of its stars, the likely outcome of its collision with your galaxy billions of years from now. You measured all of it from here, from this planet, using instruments built over a few centuries by a species that spent most of its evolutionary history as a nomadic animal with no writing, no mathematics, and no concept of a galaxy. The measurement was not handed to you. It was built, piece by piece, across generations, through the kind of sustained, cumulative, self-correcting effort that is the most distinctive and least frequently acknowledged achievement of the species you belong to. The scale is terrifying. The isolation is real. The distances are permanent. The confinement to one galaxy among 2 trillion is the fundamental physical condition of any biology operating under known laws in this universe. And nothing in the foreseeable horizon of human knowledge or technology changes that condition. But the measurement is also real. And there is something in that. Something precise, irreducible, and entirely without precedent in the history of the cosmos, as far as we can tell that no measure of physical smallness can diminish. You are small. You are brief. You are confined. You are fragile in ways the universe demonstrates constantly and without apology. And you looked up at a faint smudge on an autumn night, and you knew exactly what you were seeing. 1 trillion stars, 2.5 million light-years away, coming toward you.